Hello there and welcome to Life Beyond Seen, where curiosity eases its way into the quiet corners of the mind and science takes a slower path, one gentle enough to drift along with. Tonight we're settling into a place that very few eyes have witnessed directly, a place so distant from ordinary experience that it might as well be another world entirely. But it's not out past the stars or tucked into some faraway galaxy. It's here on Earth, hidden beneath waves that appear blue and calm from the surface while disguising something far more enormous below. We're going to explore the Philippine Trench, one of the deepest and most hostile places in the entire Pacific, a sink into the planet's crust where pressure rises to unimaginable levels and light has never had a chance to exist. Yet somehow, life finds a way to endure there, quietly, stubbornly, without any of the comforts that make the surface world feel familiar. Before we take that slow descent, I'm curious where you're listening from tonight. Are you near the coast, or somewhere far from the ocean altogether? Maybe you're inland, surrounded by trees or city lights. Or maybe you're lying down somewhere comfortable, letting the day ease itself out, listening to this as you settle in. Wherever you are, I'm glad you're here because this journey is one of those rare ones that makes the planet feel both familiar and strange at the same time. If this kind of calm exploration feels soothing or gives you a small break from everything else, I'd be grateful if you tapped that like button or subscribed. It helps this little corner of quiet science reach someone else who might also need a bit of steady company before drifting off. The Philippine Trench doesn't get as much attention as some of the more famous places in the ocean. People hear about the Mariana Trench all the time, especially when someone mentions the deepest spot on Earth. But just southeast of the Philippines lies a trench nearly as deep, one shaped by enormous forces that pull the seafloor downward and open up a long, narrow scar stretching for hundreds of kilometers. The pressure at its deepest point is so extreme that it would crush almost anything designed at the surface. The temperature drops to near freezing, and sunlight, even the faintest hint of it, can't reach down through the layers of water that separate the upper sea from the abyss. The environment is so severe that most creatures on the surface wouldn't last a second. Yet in this place, there are animals that not only survive but thrive, using strategies that seem almost unbelievable until you understand the conditions that shaped them. It's strange to think about how close this massive trench is to everyday life. People swim, fish, and sail above it without ever realizing what stretches beneath them. You could be on a calm boat ride or sitting on a beach looking out toward the horizon, and somewhere past that line the ground falls away abruptly into a drop deeper than the height of almost every mountain humans have climbed. But no matter how impossible that depth feels, the animals that live down there don't see it as unusual. For them, it's ordinary. It's home. The absolute darkness, the freezing cold, the crushing pressure, the limited food that drifts down from a world they'll never see. All of it shapes a way of living that feels very different from anything we're used to. As we ease into this story, imagine the beginning of a descent, not a dramatic one, nothing like the thrill-seeking kind you might find in a documentary with tense music and flashing lights. Instead, imagine a slow, steady slide downward, the sort of descent that gives your mind time to adjust gradually. The ocean surface above you is bright and full of movement. Waves shift quietly, fish swim in and out of view, and sunlight filters through in soft patches. But as we sink past the range where those bright colours fade, the water begins to change. The upper ocean is busy. Schools of fish flash by in groups. Coral reefs, even if we're not passing one here, are usually buzzing with life. The sunlight fuels everything. Plants grow, plankton bloom, small creatures feed on them, and larger ones feed on those smaller ones. But all of that energy depends entirely on light. Go down just a little too far, and the rules start to shift. Bright colours turn dull, shapes blur, and the animals begin relying less on sight and more on senses that seem unusual to us. Descending toward the Mesopelagic Zone, also called the Twilight area, The light dims to where only vague shapes remain. You might catch sight of small silver fish that flash briefly as they move, or slow drifting jellies that pulse with a rhythm that doesn't suggest urgency. They exist in a balance between what little light still remains and the growing darkness below. The deeper you go, the more the absence of sunlight becomes an environmental force rather than a visual detail. Sight stops being helpful. Many animals develop oversized eyes to catch what tiny amounts of light are left. Others evolve abilities that don't require vision at all. But even here, we're nowhere near the conditions of the Philippine Trench. There's a calmness to the descent when you picture it like this. Not a dramatic drop, but a gradual one. Your thoughts might drift alongside the drifting particles that move downward. Tiny flakes of organic matter fall constantly from the upper ocean. This is sometimes called marine snow. It's not literal snow, of course. It's a mix of dead plankton, organic debris, and small waste particles. It's the primary source of food for many creatures living far below. Without it, almost nothing could survive in the deepest places. Yet as we go farther down, even that steady rain of material becomes sparse. More and more of it gets eaten, broken down, or dissolved on the descent. By the time anything reaches the lower zones, what's left is minimal. But down there, even a tiny particle can matter. As we ease deeper past the point where light disappears entirely, a different kind of life begins to appear. The animals start creating their own light through bioluminescence. It's not meant to be decorative or dramatic. It's useful. Some creatures use their glow to confuse predators. Others use it to communicate. Some use light to lure prey, and some use it as camouflage in a strange way, matching the faint glow from above so predators below can't see their silhouette. But even with all of that, these glowing creatures are still far above the trench floor. The Philippine Trench lies beyond those flickers, in a realm where almost nothing glows because even bioluminescence can become a liability. As we imagine continuing this descent, the body begins to feel small against the scale of the water column. We're now passing the point where no sunlight exists at all. The temperature drops closer to freezing, but not quite. Around 2 to 4 degrees Celsius becomes the norm. It doesn't change drastically. There's no warm season or cool season here. The stability is constant, which influences how animals behave and how slowly many of them grow. But nothing about this part of the ocean is still. The water moves, though slowly. Currents shift. Particles drift. Lives unfold even when we can't see them. This journey continues downward past 6,000 meters, the boundary where the Hadal Zone begins. This is the region named after Hades, not in a dramatic or poetic sense, but simply to mark depth beyond the abyssal plains. The Hadal Zone includes the world's deepest trenches, places carved into the earth by huge tectonic forces. The Philippine Trench is one of them. It stretches for much of the eastern side of the Philippines like an enormous wound created by the subduction of the seafloor. It reaches depths of over 10,000 meters, offering conditions so extreme that even scientific equipment struggles to function correctly. Yet despite all of that, animals live here. Not just simple ones, not just microbes. Complex animals with nervous systems and behaviours survive at pressures over 1,000 times greater than those at the surface. Pressure is not just a number in this part of the ocean. It's a constant force shaping every possible feature of life. At the deepest points of the Philippine Trench, the pressure reaches more than 11,000 pounds per square inch. To put that in familiar terms, if you took all the weight of several elephants, stacked them on your fingertip, and then imagined that being a normal condition rather than an unusual one, you'd begin to understand what organisms here deal with every moment. Their bodies are flexible in ways that surface animals can't be. Their cellular structures are reinforced with molecules that prevent proteins from folding incorrectly. Their membranes stay functional despite pressures that would destroy almost anything we're used to seeing. Yet despite these harsh conditions, the creatures that live down there aren't frantic. They don't rush or panic or struggle in constant fear. Almost everything in the Hadal Zone moves slowly. The metabolism's regulated by the cold and the scarcity of food. There's no need for speed. A quick burst of motion would waste energy that might not be replenished for days or weeks. And since most predators here rely on surprise rather than speed, even hunting strategies follow the same calm, methodical logic. As we approach the idea of reaching the deepest parts of the Philippine Trench, the isolation becomes even more notable. There are no plants, there's no sunlight, there's no sound from the surface. The animals that live here have never seen a bright colour. They've never felt warm water. Their world is stable in its severity, predictable in its harshness, and yet life persists with strategies that are surprisingly effective. Some animals use transparent bodies to avoid being seen, others use gelatinous tissue that shifts easily under pressure. Some have bones so thin and flexible they would never support life on the surface but function perfectly in this crushing environment. You might imagine the trench floor as a barren desert, empty and silent. But that isn't entirely accurate. While it's sparse compared to the upper ocean, it's not lifeless. Amphipods scurry across the sediment. Snailfish drift above the ground, their bodies soft enough to withstand the conditions. Microbial mats form on certain surfaces, feeding on chemical reactions rather than sunlight. Even the occasional large carcass that drifts down can bring sudden bursts of activity, drawing in animals that may not have eaten in a long time. The existence of life in this trench is a reminder that survival isn't limited to familiar places. Life adapts, adjusts, and finds solutions to conditions that seem impossible at first glance. As we continue into this story, we'll look closely at the creatures that endure these extremes, the geological forces that shape this trench, and the mysteries that still remain hidden beneath all that water. But for now, let's keep drifting downward, easing into the depth with steady curiosity. When people think about the ocean, they usually imagine the part they can see. The surface with its shifting waves, the white foam that curls at the edges, the way sunlight skims across the top like it's just brushing the water's skin. Maybe they picture coastlines, shallow reefs, or the first few meters where swimmers and divers spend their time. What most of us don't automatically imagine is how the ocean is arranged beneath all that. It isn't simply a giant basin of uniform water. It's layered, and each layer feels like a different world with its own rules, its own conditions, and its own collection of creatures that have learned to operate within them. Moving toward the Philippine Trench means moving through these layers one by one, almost like descending a staircase that becomes dimmer, colder, and more pressurized with every step. If we start near the surface, the water is bright, and almost everything relies on that brightness. Sunlight fuels the vast majority of life here. Plants, or more specifically phytoplankton, take in the sunlight and create the foundation for the entire food system. Fish, sharks, sea turtles, whales, jellyfish, and everything else that moves freely through these sun-drenched waters depend in one way or another on that energy soaking through the first few 100 meters. For anyone who's ever looked down while snorkeling or seen a reef in clear water, this is the part of the ocean that feels familiar, even if you've never touched it directly. It's warm, it's full of activity, and it changes constantly. But as soon as we begin drifting away from the surface, the light weakens faster than most people expect. By the time we're just a few dozen meters down, the colours begin fading. Reds disappear first, then oranges, then yellows. Everything that relies on those wavelengths begins to look different, more muted, more uniform. Fish that appear brightly coloured near the surface can look entirely grey at this depth, because the wavelengths that reflect their colour simply never reach them. This shift can feel subtle at first, but the deeper we go, the more we notice how quickly the sun loses its grip on the water. At around 200 meters, the light becomes faint enough that many animals start depending on other senses, and beyond that point, sight becomes less of a priority, and adaptability takes over. Continuing the descent toward the deeper layers, the water cools steadily. It's not dramatic or sudden. It's a steady slide toward temperatures that no longer shift much with the time of day or season. The ocean has a stable, predictable thermal structure at depth. The upper warm layer, the thermocline beneath it, and then the colder layers that define the deeper zones. Each layer resists mixing with the one above or below it, and because of that, the communities of life in each region develop their own ways of living, largely independent from those outside their range. Moving below the middle zones, the feeling changes again. The animals that live here often evolve with elongated bodies, large eyes, and behaviours that seem unusual compared to surface species. Many of them migrate upward at night to feed and then return to the darkness before morning arrives. This vertical migration is one of the largest daily movements of biomass on the planet, but it goes completely unnoticed by anyone on land. It's quiet, steady, and deeply ingrained in the lives of the many fish, crustaceans, and gelatinous organisms that make the journey every day. But as we continue down, the migration becomes less common. The animals below this point don't come up for feeding trips. The pressure differences are too great. The temperature change is too abrupt, and the energy cost too high. The staircase into the deep is defined by thresholds, each more extreme than the last. Pressure, for example, increases quickly once we pass the upper layers. At the surface, pressure is roughly 1 atmosphere. Every 10 metres we descend adds another atmosphere. By 100 metres, we're at 10 atmospheres. By 1,000 metres, we're at 100. And when we're still nowhere near the bottom of the Philippine Trench, pressure has become a constant force acting on everything around us. Animals here don't have air-filled cavities the way surface creatures do. Their bodies aren't built with the same kind of rigid structures. Instead, they rely on water-filled tissues that match the pressure around them. The deeper we go, the more this becomes the standard. As we descend further, we cross into a zone where sunlight can no longer penetrate at all. This isn't something that happens gradually over miles. There's a point where even the faintest hint of dimness disappears completely. At this depth, bioluminescence becomes the only source of illumination, but it's not constant. It appears in flashes, pulses, or brief glows depending on the species. Some animals use it to hide their shadow when predators below might see their silhouette against the faint glow from above. Others use it to attract prey that mistake the light for something harmless. Some use it as a signal to others of their species, but this glowing behaviour doesn't last all the way down. In the depths of the Philippine Trench, even bioluminescence becomes rare because any light risks drawing unwanted attention. The deeper we go, the quieter everything becomes. Pressure continues to rise and temperature continues to fall, but the experience now feels different. We're no longer in the realm of creatures that migrate or actively hunt in fast bursts. Instead, we're moving through an area where slow movement is the norm. Predators take their time. Prey rarely flee in rapid spurts. Almost everything conserves energy. Food is scarce, and there's no reason to expend more effort than necessary. This slow pace doesn't come from laziness. It's a direct response to the limited resources available at depth. Every calorie must be used efficiently. The layers above are shaped by sunlight and movement, while these deeper layers are shaped by darkness and stillness. But it's not an empty stillness. The water continues to move gently. Particles drift. Microorganisms multiply. Animals shift quietly through the dark, interacting rarely but significantly when they do. There's an order here, even if it's not obvious from the outside. Approaching the lower depths, the environment transitions from the cold zones into the Hadal region. This area is defined by trenches and deep depressions formed by tectonic forces. In the case of the Philippine Trench, the forces at play involve one tectonic plate sliding beneath another. This movement pulls the seafloor downward, creating a long, narrow area that reaches depths exceeding 10,000 metres. The descent into this region is not a simple linear drop. The trench walls slope and curve, forming shelves, ridges, and steep drops. The floor is often composed of soft sediment that collects the remnants of organic material drifting downward over years. This sediment can be meters thick in some places, creating a type of cushion that covers the harder seafloor beneath. The layers of the ocean above influence life in the trench far more than the trench influences them. Almost everything that arrives at the deepest points originates from somewhere higher up. The animals in the trench rely on the limited organic material that sinks through the water column. Every piece of marine snow matters. Every small carcass that drifts down becomes an event. Because food is so restricted, life here must adapt to scarcity. But scarcity does not eliminate complexity. The creatures that endure these depths have different strategies, each tailored to the conditions of extreme pressure and limited energy. Descending along the invisible staircase that leads into the Philippine Trench means witnessing how the rules shift. Bones become less practical. Flexible cartilage becomes more common. Soft-bodied animals thrive because they don't resist the pressure that surrounds them. Some species have minimal skeletal structure. Others have biochemical adaptations that allow their proteins to remain stable, despite being squeezed by conditions that surface creatures simply could not withstand. Every adjustment is functional, shaped by necessity rather than complexity for its own sake. As we drift deeper along this path, temperature levels out at just a few degrees above freezing. There are no warm pockets. The water does not fluctuate with the seasons. This consistency creates a stable environment, even if the stability feels harsh. Many deep-sea creatures rely on these unwavering conditions. Their metabolic rates slow dramatically. Some species can live far longer than their shallow water relatives because their bodies operate at a pace that doesn't burn through energy quickly. Looking upward from this depth would provide nothing useful. There is no light to guide direction. Instead, many animals sense vibrations, chemical trails, or subtle changes in pressure. Their senses have evolved to operate without any reliance on vision. What might feel like a disadvantage on land becomes a necessity here. Being able to detect disturbances in the water helps animals locate food or avoid predators without requiring light. The deeper we go, the more the ocean feels like a place built from layers of adaptation. Each step downward adds a new requirement for survival. Creatures in the upper layers may avoid predators with speed or camouflage. Those in the middle layers rely on sensory abilities or bioluminescence. But below all of that, in the extreme depths, survival is built on efficient energy use, pressure resistance, and slow, deliberate behavior. There is no room for excess. Every adaptation must serve a purpose. As the descent continues, the water thickens in a way that isn't literal, but still feels real when you imagine it. Not because the density increases dramatically, but because the pressure becomes a defining force. Equipment designed for the surface must be engineered carefully to withstand these conditions. Materials must be chosen for strength and flexibility. And yet the animals that live here do not rely on engineering. Their tissues, membranes, and proteins have simply evolved over time to exist comfortably in a place where human-made objects require intense reinforcement. The ocean staircase into darkness is not uniform. It includes small ridges, pockets, and contours where life takes hold. Even the trench walls provide surfaces for certain organisms to cling to or forage near. There are areas rich in organic material and areas where almost nothing lands. The distribution of a life is patchy, following the patterns created by water currents and the shape of the trench floor. Throughout this descent, one thing becomes clear. The Philippine Trench is not simply the bottom of the ocean. It is the culmination of all the layers above it. Everything that lives here is shaped by the long journey that begins at the surface, where sunlight creates energy that slowly works its way downward. By the time that energy reaches the trench, it has passed through countless transformations, supporting different communities at each layer. The animals at the deepest point are the final recipients of that slow transfer. Their lives depend on the remnants that escape the consumption of the billions of organisms above them. Reaching the deepest part of the staircase does not feel like arriving at an ending. It feels like entering the final region of a vast system, one where the rules have changed so thoroughly that life looks unfamiliar but not chaotic. The Philippine Trench is the result of pressure, darkness, cold, and scarcity working together. But even here, life adapts, survives, and continues, as steady as the descent itself. The deeper we go into the Philippine Trench, the more the idea of light stops being a simple absence and becomes something the environment has never depended on. Up on the surface, even on cloudy days, light is always part of the equation. It shapes daily cycles, feeds entire food systems, and gives structure to how living things behave. But below the upper layers of the ocean, there is a point where light isn't just dim. It's gone. Not weakened or reduced or filtered. Gone in a complete and permanent way. And once we pass into that region, we enter a world where everything alive has adapted to a lifetime without sight of the sun, without colour, without anything that resembles the conditions at the surface. This isn't a place where light used to exist. It's a place where it has never been. The transition happens gradually as we descend, but it eventually reaches a threshold that is absolute. Sunlight, even at its brightest intensity near the surface, can only penetrate so far. Water absorbs and scatters it, capturing the photons long before they could ever reach the Hadal Zone. This means the deep doesn't feel like nighttime or a shaded room or a cloudy day. Those comparisons rely on the idea that light exists nearby, waiting to return. Down here, light has no presence at all, and there is no expectation of it. The creatures that survive in this region live in conditions that are permanently dark, without a dawn or dusk to structure their perception of time. Without sunlight, the environment becomes defined by what does remain. Pressure, cold, and the slow drift of organic particles shape the entire ecology. Vision becomes an unnecessary and sometimes impossible sense. Many animals have no eyes, or they have eyes that never develop into functional organs. Others retain their eyes, but the eyes are reduced to small clusters of cells that detect faint changes in their surroundings without forming images. The central importance of sight at the surface becomes irrelevant here. Instead, animals rely on sensory systems that function without light. Some rely on vibrations. Movement in the water can travel much farther than light, so the animals in these depths often detect their surroundings through slight shifts in the water column. A distant disturbance from a sinking carcass, a slow glide of another animal, or even the subtle drift of marine snow can alter the flow around them. These shifts become signals, markers of presence, and indicators of when to move, when to feed, and when to remain still. Other animals depend on chemical cues. The water carries traces of decaying organic matter, waste, or the presence of other organisms. This chemical information can reveal whether food is approaching or drifting away, or whether another creature is close enough to pose a threat. Chemical sensing in the deep works as a kind of long-range awareness that doesn't rely on light or sound. A smaller group of animals still uses bioluminescence, though it becomes less common with each step downward. In the midwater zones, many species glow regularly, but in the depths of the Philippine Trench, bioluminescence poses risks. Producing light costs energy, and energy is extremely limited. It also reveals the animal's position, which can draw predators from the surrounding darkness. Some species still use faint glows, but these displays are often minimal and targeted. A small flash to distract a predator, a short pulse to signal to a mate, or a dim glow used to startle prey may appear now and then, but they are rare. Most of the time, the darkness remains unbroken. Because light has never played a role in shaping this environment, the animals here evolved without any reliance on it. Their bodies and behaviours reflect the demands of this world. Many species have soft, flexible bodies because rigid structures resist pressure. Soft-bodied animals can withstand incredible compression without damage. The lack of light also changes the ways their features develop. Colour serves no function, so most animals appear pale, transparent or uniform in tone. Patterns, shapes, and markings that matter near the surface disappear. Evolution doesn't bother maintaining traits that have no advantage in this environment. This world is also cold. Temperatures hover just above freezing, and without sunlight, there is no warmth other than what organisms generate internally. Cold slows down chemical reactions, metabolic processes, and growth rates. Many deep-sea animals grow slowly, reproduce infrequently, and live longer compared to their shallow water relatives. Slowness isn't a disadvantage here, it's efficient. Energy must be used carefully, and anything that saves energy becomes an advantage. Food scarcity defines this world even more than darkness does. Since no sunlight reaches the deep, no plants or phytoplankton can grow here. The animals rely entirely on what falls from above, and the amount of material decreases with each meter it travels downward. Marine snow begins as a mixture of organic debris near the surface, but by the time it reaches the Hadal zone, much of it has been consumed by organisms in the upper layers. What makes it to the trench floor is minimal, and so the creatures here have adapted to survive on very small amounts of nutrients. Occasionally larger food sources arrive. A whale carcass, for example, can wander downward for days before finally reaching the trench floor. When it does, it creates a local surge of activity. Animals that may not have fed properly in weeks or months suddenly have access to a large resource. Amphipods, snailfish, and various scavenging organisms gather around to feed. Microbial communities colonize the bones and soft tissues. Over time, the carcass becomes integrated into the nutrient cycle. Events like these are rare but significant, shaping the dynamics of life in the deep. Even without large food falls, the animals adapt their bodies to reduce the need for constant feeding. Some species maintain minimal muscle mass, relying on slow movements. Others can store nutrients in specialized tissues. Several fish in the deep trenches possess gelatinous bodies that require little energy to maintain. Their muscles are thin, and their bones are often reduced or absent. Yet these traits aren't signs of weakness. They serve the demands of living where food is limited and pressure is extreme. The darkness also influences how animals navigate and understand their environment. Without light, the sense of direction becomes tied to gradients in pressure, temperature, and chemical composition. Vertical movement carries risk because pressure changes rapidly. Some species inhabit specific depth ranges and rarely stray from them. Others can move upward or downward more freely, but they do so gradually, avoiding sudden changes that could cause physical stress. The trench itself has a shape that influences where life can settle. The steep walls create slopes where some organisms can attach or burrow. The loose sediment at the bottom provides a soft surface that collects organic matter. Water movement along the trench walls and floor helps distribute nutrients, though at a slow pace. This circulation supports microbial communities that form the foundation of life at these depths. Microbes break down what little organic material arrives, releasing nutrients that other organisms can use. In this world without light, microbial life becomes especially important. Some microbes do not rely on organic material from above at all. Instead, they use chemical energy from interactions between minerals and seawater. These processes can sustain life even when no external food arrives. In places where the trench walls expose certain geological formations, microbes colonize the surfaces and form patches of activity. They become a quiet but crucial part of the ecosystem, allowing animals that feed on them to survive in conditions that would otherwise offer nothing. The absence of light also affects how animals develop. Larval stages of some deep-sea species drift upward into shallower waters before settling into the deep, but many remain entirely within the midwater or deep zones throughout their development. Their life cycles adapt to ensure that each stage can function in darkness. Eggs may be laid near the seafloor, attached to rocks or buried in sediment. Juveniles often resemble smaller versions of adults, minimizing the need for dramatic transformations. This reduces the risk of developing features that would be useless in the dark. The constant pressure reshapes biological design in subtle ways. Proteins, for example, can lose their structure under high pressure, but deep-sea animals produce molecules called piezolites that help stabilize them. These molecules prevent proteins from unfolding, ensuring that the animal's cells function properly. Without piezolites, life at these depths would be impossible. Membranes also adapt, remaining flexible even under extreme compression. These adaptations highlight how deeply the environment influences every aspect of biology here. In the absence of light, communication changes as well. Animals may use vibrations, chemical signals, or subtle movements to interact with one another. Sound travels well through water, but many deep-sea species lack the organs needed to create or detect complex sounds. Instead, they rely on indirect communication, interpreting changes in the water around them. An approaching predator may create a shift in water flow. A potential mate may emit a chemical signal. Even these small cues become essential tools for survival. Movement through this world is slow and purposeful. Animals rarely waste energy fleeing long distances or chasing prey at high speeds. Predators often wait in place for opportunities. They use minimal energy until a potential meal comes close enough to capture. Prey species, in turn, rely on stillness, blending into the background not through coloration but through the absence of movement. In the dark, being unnoticed means avoiding detection through vibrations or chemical trails rather than through sight. Despite the absence of sunlight, the environment is not silent in a biological sense. Life here is active, though in ways that differ from the patterns we recognize near the surface. The deep trench hosts communities that persist through long periods of scarcity. They survive not because conditions are easy, but because they are predictable. Pressure does not fluctuate. Darkness does not change. Temperature remains stable. In these consistent conditions, life adapts and continues. The absence of light does not mean the absence of structure. The animals in this region have stable patterns of movement, feeding, and reproduction. They respond to changes in the water column, even if those changes are minimal. The drifting of organic particles, the occasional arrival of a large food source, the slow redistribution of nutrients by microbial activity, and the gradual shifts caused by tectonic movement all shape the daily reality of this world. As we explore this place, the contrast with the surface becomes increasingly clear. Up above, life depends on cycles of light and dark. Plants grow and die with the seasons. Animals migrate, breed and feed according to rhythms shaped by sunlight. Weather changes, temperatures rise and fall, the presence or absence of light influences everything. But in the Philippine Trench and other deep-sea environments, these cycles have no impact. Life persists without sunlight, day or night, seasons or storms. The organisms living here are not remnants of a past age. They are not simplified or primitive forms of surface life. They are highly adapted to a world with stable conditions that differ from anything humans experience. Their traits are as specialized and as sophisticated as those of any surface species. Evolution does not favor complexity for its own sake. It favors traits that allow survival in specific environments. The traits of deep-sea organisms are suited perfectly to a world without light, without warmth, and without abundant food. In this darkness, the absence of visual cues creates opportunities for other senses to take precedence. Chemical and mechanical sensing allow animals to navigate, feed, and reproduce effectively. The lack of light is not an obstacle to overcome. It is simply another environmental condition that shapes life. Moving through this environment makes it clear that light is not a requirement for life, only for the kind of life we're most familiar with. In the Philippine Trench, existence continues in the quiet and consistent dark, shaped by pressure, cold, and scarcity. The animals that live here are not waiting for light to return. They have evolved for a world that has never known it. Moving deeper into the Philippine Trench means entering a realm shaped almost entirely by pressure, a force so constant and overwhelming that it defines everything living there. It's difficult to imagine pressure without actually experiencing it, because nothing on land comes close. Even the deepest parts of lakes or the densest pockets of the atmosphere feel gentle compared to what exists in the Hadal Zone. At the surface of the ocean, the pressure on your body is about 1 atmosphere, the same pressure of the air around us every day. It's enough to keep us comfortable and allow our bodies to function normally. But with every 10 meters of descent into the ocean, another atmosphere of pressure is added. That means at just 100 meters, the pressure is 10 times what we're used to. At 1,000 meters, 100 times. And in the deepest reaches of the Philippine Trench, over 10,000 meters down, the pressure exceeds 1,000 atmospheres. If that number feels abstract, it may help to imagine how ordinary objects behave when pressure increases. A simple metal cylinder, strong and rigid on land, collapses into itself when taken to depth that would crush it like crumpled tin. Air pockets implode immediately because air compresses easily, and no container built casually at the surface can resist the force of the water at depth. Even specialized equipment engineered for deep-sea exploration struggles. The walls of deep submergence vehicles must be thick and precisely shaped to distribute pressure evenly. Any flaw, even a small one, can put the entire structure at risk. This isn't simply a matter of strength, it's a matter of design shaped entirely to accommodate the force applied from every angle at once. The water pressing down on the deepest parts of the trench doesn't feel like a downward force the way gravity does on land. It surrounds everything, pushing inward uniformly. Unlike atmospheric pressure, which decreases with altitude and increases with depth only slightly if you climb mountains or descend into valleys, hydrostatic pressure in the ocean increases rapidly and consistently. At extreme depths, it becomes an inescapable part of the environment. Any creature that survives here must be able to withstand pressure that would crush bones, collapse lungs, and cause most biological tissues to fail almost instantly. The animals that live in the Philippine Trench evolved not to resist pressure in the way a reinforced vehicle does, but to exist within it as though it were normal. Their bodies are not built to push back. Instead, they avoid any structures that would create vulnerability. Most have very few or no air-filled spaces. Air pockets are liabilities in high pressure because they compress easily and can collapse tissues around them. Fish that live near the surface have swim bladders to regulate buoyancy, but deep-sea fish, including those in the trench, usually lack them. Without a swim bladder, they rely on oils, specialized proteins, or gelatinous tissues to maintain balance in the water column. The bones of deep-sea species, when they exist at all, are thinner and more flexible than those of surface-dwelling relatives. Instead of rigid skeletons, many creatures rely on cartilage or soft connective tissues that can deform under pressure without breaking. This makes movement slower and less forceful, but in an environment where speed is rarely required, the trade-off is worthwhile. Flexibility becomes a survival strategy. Rigid structures resist pressure and fail. Flexible ones absorb it and continue functioning. Cells, too, must adapt to the crushing force. Cell membranes risk becoming too rigid under pressure, which interferes with essential processes like nutrient transport and communication between cells. Deep-sea organisms compensate by altering the composition of their membranes. They incorporate more unsaturated fatty acids, which remain fluid even at low temperatures and high pressures. This allows their cells to function normally despite the conditions. Proteins inside cells require special attention as well. High pressure can cause proteins to lose their shape, a process called denaturation. When proteins unfold, they lose their ability to perform their jobs, which can be catastrophic for the organism. To counter this, deep-sea species produce stabilizing molecules called piezolites. These molecules help proteins maintain their structure under pressure. Without them, life at extreme depths would not be possible. The pressure also affects the behavior of water itself. Water becomes slightly denser under extreme pressure, and this density influences how sound travels, how chemicals diffuse, and how organisms move. Sound can travel long distances in the deep ocean because the water is uniform and dense, but many deep-sea animals lack specialized hearing structures to take advantage of this. Instead, they detect vibration and movement through their bodies, sensing the flow of water around them. This is often more useful than sound because movement carries immediate information about potential threats or food sources. The trench floor, where the pressure is highest, presents unique challenges. The sediment is soft, and the weight of the water above compresses it into a dense, fine layer. Animals that burrow must navigate sediment that behaves differently from sediment found in shallower regions. Microorganisms often thrive here because they can survive in compacted environments. Breaking down organic material that arrives from above, larger organisms that interact with the sediment do so carefully, using slow, deliberate movements to avoid sinking into the soft surface. Pressure shapes every movement. A sudden burst of speed uses too much energy and risks structural strain. Slow, controlled motions are safer and more efficient. Many animals drift or glide rather than swim actively. Their gelatinous bodies, which may seem fragile on the surface, actually provide stability under pressure. The water around them supports their weight, and their soft tissues are not prone to damage. Despite the extreme conditions, the deep sea is not a uniform environment. Pressure is constant, but other factors vary. Slight differences in temperature, oxygen levels, and the availability of food create microhabitats. Some areas have more organic material due to the way currents flow along the trench walls. Others have geological features that influence the distribution of nutrients. These variations create small pockets where certain species thrive more than others. Pressure also influences reproduction. Many deep-sea animals produce fewer offspring than their shallow water relatives. They invest more energy in each egg or larva because survival rates are low in such a harsh environment. Some species lay eggs in protected areas, such as cracks in the trench walls or deep crevices where pressure remains constant and the eggs are shielded from predators. Development is slow, often taking months or even years, but slow development is normal in the deep sea, where energy conservation is essential. Even with all these adaptations, the animals of the Philippine Trench must contend with occasional disturbances. Earthquakes are common in subduction zones, and the trench is no exception. The movement of tectonic plates can shift sediment, alter local topography, and disturb the flow of organic material. For creatures accustomed to stability, these disturbances can introduce sudden challenges, but many species respond by adjusting their position, burrowing deeper, or temporarily retreating into sheltered areas. The ability to handle infrequent disruptions becomes part of their survival strategy. Pressure also affects human attempts to explore the trench. Deep-sea probes and submersibles must be engineered with great care. Spheres made of thick metal or specialized composite materials house instruments and cameras. These spheres are shaped precisely so that pressure distributes evenly across their surfaces. Flat surfaces tend to fail under high pressure, so engineers design them with curves that minimize weak points. Even with careful design, equipment can malfunction. Pressure can cause leaks, crush components, or interfere with electronics. Every mission into the trench requires meticulous planning and testing to ensure that instruments survive the descent. Data gathered from these explorations reveals just how remarkable the adaptations of deep-sea life truly are. For example, snailfish found in the depths of trenches have soft, translucent bodies with thin bones. Their muscles are adapted to generate small but sustained movements. Their cells contain high levels of piezolites, and their membranes are suited for stability at extreme pressure. They seem delicate when viewed in submersible footage, but in their environment, they are well equipped to survive. Amphipods living in the trench show similar adaptations. Their exoskeletons contain lower levels of minerals, making them more flexible under pressure. They can process organic material that arrives at the seafloor with great efficiency. Their bodies have biochemical tools that protect proteins and maintain cell integrity. These amphipods are often some of the first animals to investigate new food sources that fall into the trench. Their activity helps distribute nutrients and supports the broader ecosystem. Pressure even influences the microbiology of the trench. Microbes adapted to high pressure are called piezophiles. They grow best under conditions that would inhibit or kill most organisms. Some piezophiles use chemical reactions involving minerals in the sediment to generate energy. Others rely on the breakdown of organic material. These microbes form the foundation of the deep-sea food web. Without them, larger organisms would struggle to access the limited nutrients available. The consistency of pressure in the deep sea creates a predictable environment, even if it seems harsh from a human perspective. Unlike the surface, which experiences storms, seasonal changes and temperature variations, the deep remains stable. Animals that live here rely on this stability. They evolve slowly, and their traits persist across long periods. Sudden environmental changes would be far more harmful here than on the surface. That stability becomes a resource that organisms depend on as much as the scarce nutrients. The idea of an impossible realm doesn't come from exaggeration. It comes from comparing what exists here with what we know on land. Our bodies cannot withstand such pressure. Our equipment struggles. But the life down here is not only capable, it is suited to the environment in ways that demonstrate the flexibility of evolution. Pressure doesn't eliminate life, it shapes it with precision. The creatures of the trench do not perceive the pressure as oppressive. They have never known anything else. For them, this force is not a barrier, it is simply the environment. Their bodies and behaviours reflect the conditions because those conditions are constant. The adaptations they carry are not temporary solutions, they're permanent features shaped by millions of years. As we continue exploring this realm, the relationship between pressure and survival becomes clearer. Everything in the Philippine Trench is influenced by it, from the smallest microbial cell to the largest scavenging organism. The pressure isn't just a background condition, it's the defining feature of life here. And moving onward, we'll look more closely at the creatures that illuminate the dark, not with light, but with the way they live under these relentless conditions. As we move farther into the Philippine Trench, we arrive at a zone where the darkness becomes so complete that light can only exist if organisms create it themselves. Even though this region is far darker than anything familiar, life here has developed ways to generate the faintest of glows. These glimmers aren't bright enough to illuminate the environment in the way surface light does, and they certainly aren't meant to reveal broad landscapes. Instead, they exist as small signals, brief flickers, or controlled pulses that serve specific purposes in a world where sight has little value. The glow doesn't replace sunlight. It simply offers pockets of function that allow certain species to communicate, feed, or avoid threats in an environment where nothing external shines. This glow is called bioluminescence, and it comes from chemical reactions inside an organism's body. Two main components, luciferin and luciferase, interact to produce light. The details vary between species, but the general principle is consistent. What makes bioluminescence remarkable in these depths is not its brightness, but its efficiency. Producing light requires energy, and energy is limited here. That means these animals have evolved extremely precise ways of using it, ensuring that every glow serves a purpose. In the depths surrounding the trench, bioluminescence is far more common than in the trench floor itself. The creatures that inhabit this region must balance the benefit of producing light with the risk of revealing their position. Above these depths, many species use bioluminescence freely because predators and prey rely more on sight. Down here, where light is nearly absent, too much glow can draw unwanted attention. As a result, the patterns of bioluminescence become subtle. Small pinpoints of light might appear on the bodies of certain fish. A quick flash might signal a warning. A narrow band of faint illumination might outline the underside of an animal to help it blend in with the faint light from far above, making it harder for predators below to detect its silhouette. Even though the Philippine Trench is one of the deepest points in the ocean, there are still zones above the trench floor where bioluminescent organisms play a major role. These creatures populate the mid-water layers that form the transition between the areas where bioluminescence is common and those where it becomes rare. Each species uses its glow differently. Some deploy simple dots of light, while others have complex arrangements of organs that can be controlled individually. These organs, called photophores, act like tiny lamps that the organism can switch on or off. The way they are arranged often matches the specific needs of the species. For instance, certain deep-sea shrimp release a bioluminescent cloud when threatened. Instead of producing light from their bodies alone, they eject a cloud of glowing chemicals that distracts predators. As the cloud expands, it creates a confusing display that allows the shrimp to escape. This strategy is effective because predators in the deep rely heavily on motion to identify targets, and the shifting light confuses them long enough for the shrimp to move away. Some deep-sea fish have evolved a different strategy. They produce small glows under their bodies to mimic the dim light that filters down from above. Even at these depths, a faint trace of illumination from far-off sources can penetrate slightly. Predators looking upward use this faint glow to detect the outlines of prey. But if a fish can match this glow with light of its own, it effectively masks its silhouette. This tactic, known as counter-illumination, allows the fish to blend into the background. It's a subtle use of light, not for communication or offense, but for concealment. Another group of animals uses bioluminescence in more active ways. Some species have glowing lures that attract prey. The anglerfish is one of the better-known examples. A small glowing tip on an extended spine near its head entices potential prey to come closer out of curiosity. In the darkness, the lure stands out as an unusual object, drawing the attention of smaller animals. When they approach, the anglerfish snaps its jaw shut quickly, using a combination of speed and pressure, resistant design to capture its meal. The lure is effective because it provides the only visible point in an otherwise featureless environment. There are also animals that use their glow to coordinate movements within groups. While the Hadal Zone is known for sparse populations, some midwater species form loose gatherings. A brief flash can serve as a cue to maintain distance, adjust positioning, or respond to the movement of the group. These signals are efficient, simple, and easily recognized by others of the same species. They don't illuminate the water around them. Instead, they produce momentary bursts that deliver information quickly without wasting energy. As we descend closer to the trench floor, bioluminescence becomes less common. The animals that inhabit the deepest regions do not rely heavily on glowing displays because almost any light can be hazardous. Predators at the trench floor often depend not on vision but on vibration and chemical signals. Light can reveal an animal's position to nearby organisms that might interpret it as a cue to investigate. As a result, many species in the deepest parts of the trench have evolved reduced or absent bioluminescence. If they produce light at all, it tends to be controlled in extremely precise ways. Nevertheless, there are still examples of bioluminescent organisms even at great depths. Some microbes produce faint glows as part of their metabolic processes. These glows are not visible to human eyes through submersible cameras because they are too dim and too small in scale. However, they play a role in the microbial ecosystem. The interactions between these microbes and larger organisms remain an area of active scientific investigation. The deep sea, including the trench environment, contains microbial life that scientists continue to study for insights into how life can adapt to extreme pressure and darkness. Even though the light produced by deep-sea organisms is faint, it has a profound impact on how animals interact. The ability to produce light in an environment where visibility is minimal allows species to develop strategies that would otherwise be impossible. A glowing lure, a distracting flash, or a series of small points along the body can influence survival in ways that are subtle but effective. The glow serves as a tool that fills the niche left vacant by the complete absence of sunlight. The bioluminescent creatures in this region tend to have specialized organs that operate under strict control. These organs often contain layers of reflective material that direct light outward. The organism can regulate the chemical reactions that produce the glow, turning the light on or off as needed. Some species can regulate the intensity, allowing them to produce a barely visible glimmer or a brighter flash. This level of control is essential. In these depths, uncontrolled light would be dangerous. The glow these animals produce is usually blue or green because these wavelengths travel farther through water than red or yellow. Blue light penetrates the water more effectively, even at great depths. As a result, bioluminescent organisms evolved to use light in this range. But the glow is still limited, often visible only within a few meters. Beyond that distance, it fades into the darkness. This limited visibility is precisely what makes bioluminescence useful here. It provides close-range communication or strategic advantages without exposing the animal to unintended threats. Some deep-sea squid can produce patterns of light along their bodies. They use these patterns to escape predators, flashing rapidly to create confusion. Their movements and the shifting glows make it difficult for predators to track them. This strategy can create enough disorientation to allow the squid to slip away. Even though these squid are not common in the Hadal Zone itself, similar strategies are used by species that inhabit areas above the trench. Not all animals that glow do so as part of an active behaviour. Some organisms, particularly small ones, produce light as a byproduct of their biological processes. These glows are often faint and constant. They don't serve as signals or defensive tools. Instead, they are simply part of the organism's metabolism. These faint glows contribute to the overall distribution of bioluminescence in the deep sea, though they rarely influence interactions between larger animals. As we imagine the progression deeper into the trench, the presence of bioluminescence becomes an indicator of how different the environment is from the surface. Up in the sunlit layers, colour dominates. Fish use bright markings for courtship displays, camouflage or warnings. Coral reefs are filled with patterns that rely on light. Here in the depths, colour disappears. Glow replaces colour, not through vivid displays but through minimal, functional points of light. Bioluminescence is a substitute that fills a functional gap left by the inability of sunlight to reach these depths. However, it's important to note that bioluminescence is not universal. Many species in the deep sea never evolved the ability to produce light. They rely entirely on non-visual senses. For them, the dark environment does not require any kind of glow. These animals live in a world where vision is unnecessary, and their evolutionary paths reflect that simplicity. The absence of bioluminescence in many deep trench species demonstrates the range of strategies that exist. Light is one tool among many, not a requirement. Scientists studying the Philippine Trench and other deep-sea environments continue to discover new species with unique light-producing abilities. Submersibles equipped with sensitive cameras capture brief glows that provide glimpses into ecosystems that have existed in this darkness for millions of years. These observations help researchers understand how bioluminescence evolved and how it continues to influence life in the deep. One interesting aspect of bioluminescence is that it can reveal the presence of organisms long before they are physically seen. A pulse of light in the dark may indicate a fish passing nearby, or a predator responding to movement. Researchers often observe small flashes that suggest the presence of animals too distant to be seen by cameras. These glows form a kind of indirect observation method. Scientists can infer the behaviour and movement patterns of deep-sea creatures based on the timing and location of bioluminescent events. The energy efficiency of bioluminescence is another important factor. Light produced by chemical reactions is far more efficient than artificial light sources. Organisms in the deep sea have perfected this efficiency because it ensures that the energy spent producing light serves a meaningful purpose. The reactions occur at the molecular level, and the organism controls them precisely. This efficiency becomes crucial in an environment where energy must be conserved. As we consider the creatures that glow in the deep sea, it becomes clear that bioluminescence is not a decoration or a spectacle. It is a practical tool, used sparingly and with precision. The light produced is not intended to illuminate surroundings but to influence behaviour in subtle ways. A small flash may deter a predator, a glowing lure may attract prey, a faint outline may help an organism blend with the limited light above. The Philippine Trench, due to its extreme depth, contains fewer bioluminescent organisms at the bottom compared to shallower deep-sea regions, but the mid-water layers above it are filled with species that rely on controlled glows. These creatures demonstrate the range of adaptations that life can achieve when living in darkness. Their glows act as signals in a communication system that evolved entirely without sunlight. As we move toward the next stages of the journey, these brief points of light become reminders of how adaptable life can be. Even in a realm where the surrounding environment seems to strip away most familiar structures, organisms find ways to navigate, survive, and interact. As the descent through the Philippine Trench continues, the environment becomes so extreme that it challenges one of the most basic ideas we tend to associate with animals having a defined structure. On land, and even in shallower oceans, skeletons or rigid frames help bodies keep their shape. Muscles attach to bones. Bones provide leverage for movement. They protect organs and create a stable form that resists gravity. But in the deep sea, especially in the Hadal Zone, the rules shift. Gravity doesn't shape bodies in the same way because the surrounding water supports weight. Pressure becomes the dominant force, applying equal intensity from every direction. In this world, a rigid frame isn't an asset, it's a weakness. And so the creatures that live here developed a range of strategies that allow them to survive without being crushed. Pressure is the central physical challenge in the deepest parts of the trench. At these depths, any structure that traps air becomes a liability. Air compresses easily. A fish with a swim bladder, for example, cannot descend far past the upper ocean. The bladder collapses, distorting the fish's internal organs and making survival impossible. That's why virtually no fish in the deep trench have swim bladders. Instead, they maintain buoyancy using different methods, including oils, lipids, or changes in body composition. These strategies allow them to remain neutrally buoyant without relying on structures that would fail under pressure. Bones follow a similar pattern. Rigid bones are more vulnerable because they resist compression rather than adjusting to it. Surface fish have dense, mineralized skeletons that can withstand normal pressures. But in the deep ocean, heavy mineral content becomes a disadvantage. Pressure pushes inward from all sides. A rigid skeleton resists unevenly, creating points where force accumulates. This can lead to fractures or complete failure. To avoid this, many deep-sea species reduce their bone density. Some have skeletons that are thin and lightly calcified. Others have skeletons made mostly of cartilage rather than hard bone. One of the most remarkable examples of adaptation is the Hadal snailfish. Discovered in several deep trenches, including the Mariana and Kermadec trenches, it also has relatives living in the Philippine Trench. These fish look delicate, with bodies that appear almost translucent. They don't have the strong muscles or thick bones of shallow water fish. Instead, they rely on a flexible gelatinous structure. Their skulls are reduced, their ribs are minimal, and their overall shape is supported mostly by cartilage. This might seem fragile from a surface perspective, but in the deep ocean, it's an ideal design. Soft tissues bend with the pressure rather than resist it. Flexibility becomes a form of strength. The snailfish's muscles are adapted to operate efficiently at high pressure as well. Surface fish often rely on fast twitch muscles for quick bursts of motion. But deep-sea snailfish use slower, more energy-efficient muscle fibers. These fibers allow the fish to move deliberately, using small motions to navigate the water without expending unnecessary energy. Their bodies are not built for speed or agility. They're built for stability in an environment where sudden movements are rare. The skin of deep-sea animals also adapts to the pressure. Many species have soft, gelatinous skin that offers little resistance. This minimizes the stress placed on the body. Some animals have thick layers of mucus or gelatin to create a buffer between their tissues and the water around them. These layers don't prevent pressure from reaching the body. They simply allow the body to adjust without damage. In a way, the softness becomes a protective measure against compression. This principle extends to organs as well. Most deep-sea fish have reduced or absent swim bladders. Their hearts and digestive systems operate at slower rates. Their livers may contain large quantities of oils that help with buoyancy and also protect tissues from pressure. Their brains are smaller and more compact, reducing the risk of pressure-induced deformation. Every organ must be able to function under conditions where even minor structural weaknesses could cause failure. Gelatinous bodies are not limited to fish. Many invertebrates in the deep sea rely almost entirely on soft tissue. Jellyfish, for example, thrive in deep water because their bodies contain a high percentage of water and minimal rigid structure. The pressure doesn't crush them because there's nothing to collapse. Their internal composition matches the density of the surrounding water, allowing them to drift easily. This strategy works so well that many deep-sea organisms follow similar patterns, even if they aren't closely related to jellyfish. Certain deep-sea worms also develop soft, elongated bodies. These worms burrow into the sediment or move slowly along the trench floor. Without rigid skeletons, they adjust to the pressure naturally. Their bodies compress evenly and expand again if pressure changes slightly. Their tissues are supported by hydrostatic pressure, where internal fluids provide stability against the external force. This method is efficient and avoids the risks associated with rigid internal structures. Crustaceans present an interesting case because many species typically rely on hard exoskeletons. In the deep sea, however, the composition of these exoskeletons changes. Amphipods living in the trench often have exoskeletons with reduced mineral content. The reduction makes the exoskeleton more flexible and less brittle. Calcium carbonate, a stiff and easily fractured material, is minimized because it becomes unstable at high pressure. Instead, these crustaceans incorporate more proteins and flexible structures that allow their bodies to withstand the environment. This flexibility also makes them more agile in their movements near the seafloor, where they scavenge for food. Some amphipods found at extreme depths have been discovered with aluminum in their exoskeletons, absorbed from the surrounding environment. Researchers believe this aluminum may help protect the amphipod's shells from dissolving due to the high pressure and low pH of the deep sea environment. The incorporation of aluminum is not seen in shallow water relatives, which shows how specific these adaptations are to trench habitats. Even the smallest organisms must adapt to avoid being crushed. Microbes that live in the trench, known as piezo-philes, have cell walls and membranes designed to remain stable under pressure. Their proteins are structured differently from surface microbes, preventing them from unfolding under pressure. These adaptations are microscopic, but they are just as critical. Without them, the foundation of the deep-sea food web would collapse. Despite the dominance of soft tissues, there are animals in the deep that retain some rigid structures. However, these structures are usually small and located in areas where they can be reinforced or supported by surrounding tissues. Some fish retain small bones in their skulls to protect their sensory organs, but these bones are often thin and flexible. The trade-off between rigidity and flexibility reflects the balance needed to survive at great depth. Another aspect of survival in the trench involves how animals move. Movement requires muscle contraction, and muscles must function properly under pressure. Deep-sea species have muscle fibers adapted for slow, steady movement, rather than rapid bursts. These slow twitch fibers allow for efficient use of energy. Since food is limited, conserving energy becomes a priority. Muscles that contract slowly and steadily use far fewer resources and place less stress on the skeleton or soft tissues. The ability to withstand pressure also influences how animals feed. Many deep-sea predators have large mouths relative to their body size. This adaptation allows them to consume prey that may be infrequent but valuable. Their jaws are often flexible, extending to accommodate larger prey. Loose connective tissues and reduced bone structures help facilitate this expansion. The pressure that surrounds them supports their soft tissues during feeding, preventing damage. Some species use suction feeding, drawing prey into their mouths with a quick intake of water. Suction feeding is particularly useful in the deep sea because it doesn't require rapid lunges or strong jaw pressure, Instead, it relies on controlled muscle contraction. This method places minimal strain on the body and works well for soft-bodied animals. The pressure helps prevent the body from collapsing inward during suction, making the technique efficient and safe. In addition to feeding strategies, deep-sea animals must be able to reproduce under high pressure. Reproduction involves delicate processes such as egg development, fertilization, and larval growth. In the trench, these processes occur under intense compression. Some species lay eggs with tough, flexible membranes that resist deformation. Others release larvae that are already adapted to high pressure. The larvae of certain species may drift upwards slightly to develop in milder conditions, but many remain within the deep layers. Their development is slow, reflecting the slow pace of life in the Hadal zone. A key part of avoiding physical damage in this environment involves the chemistry of cells. High pressure can interfere with the function of enzymes, the molecules that drive cellular reactions. To prevent this, deep-sea animals have developed versions of enzymes that remain active under pressure. They also contain molecules that stabilize cellular structures. These biochemical adaptations allow cells to function normally when they would otherwise fail. The same principle applies to membrane stability. Under high pressure, membranes can become too rigid. Deep-sea species prevent this by incorporating unsaturated fats into their membranes. These fats keep the membranes fluid, even in cold temperatures and high pressure. Without this adaptation, essential processes such as nutrient transport and communication between cells would be impaired. Pressure also influences how blood and circulatory systems function. In the deep sea, animals do not experience rapid changes in pressure because they rarely move quickly upward or downward. Their circulatory systems are designed to operate within a narrow range of pressure conditions. Blood vessels may be thinner or more flexible, reducing the risk of damage. Some species rely more heavily on diffusion, reducing the need for complex circulatory structures. Even sensory systems must adapt. Vision is often reduced or absent in deep-sea species. Instead, animals rely on pressure-sensitive organs, chemical receptors, or vibration detection mechanisms. These senses do not require rigid structures. Soft tissues support them effectively. Some species have long, thin appendages that help them detect movement in the water. These appendages are flexible and can withstand pressure without breaking. One of the most distinctive features of deep-sea life is the prevalence of gelatinous animals. Deep-sea jellyfish, comb jellies, and other soft-bodied creatures dominate the water column. Their bodies contain large amounts of water and minimal protein. This composition allows them to survive without the risk of crushing. The pressure simply passes through their tissues, causing no harm. Their simple structures are advantageous here, allowing them to float effortlessly and capture small particles or prey using tentacles or sticky cells. Another interesting example is the holothurian, or sea cucumber. Many species of sea cucumbers live in the deep ocean, including trench environments. Their bodies are soft and elongate, with flexible skin supported by collagen fibers. These fibers can adjust tension, allowing the animal to stiffen or relax parts of its body. This ability helps them move along the seafloor, ingest sediment, and expel waste. Their internal water vascular system distributes fluid pressure evenly, acting as a hydraulic skeleton. This system functions exceptionally well under high-pressure conditions. Some deep-sea starfish and brittle stars also survive in trench environments. Their bodies contain ossicles, small calcified structures embedded in soft tissue. These ossicles provide support without forming rigid skeletons. Because the ossicles are scattered and flexible, they can withstand the surrounding pressure without fracturing. The animal's arms remain capable of slow, deliberate movement, helping them forage along the sea floor. All these adaptations demonstrate a key principle. In the deep sea, the best way to avoid being crushed is to avoid resisting pressure directly. Instead of opposing it, deep-sea animals let the pressure surround and support them. Their bodies match the density of the water. Their tissues and structures allow compression without damage. Their internal chemistry keeps cells functioning despite the intense conditions. What might seem fragile in shallow water becomes efficient at great depth. Soft bodies thrive where rigid ones fail. Flexible skeletons outperform strong ones. Gelatinous tissues become more useful than muscles built for speed. The Hadal Zone rewards animals that adopt these strategies. As we continue moving through this environment, the adaptations that allow life to exist under pressure become part of a larger picture. These organisms not only survive, but fulfill roles that keep the ecosystem functioning. Their bodies, their behaviours, and their chemistry reveal how life responds to one of the most challenging environments on Earth. As we settle deeper into the Philippine Trench, the question of how anything survives in such an isolated environment becomes more pressing. Without sunlight, plants cannot grow. Without plants, there is no base for a typical food chain, and yet, life not only exists here but persists in steady patterns that have continued for millions of years. The answer lies in a process happening far above, in the bright waters near the surface. Everything that lives here, from the smallest microbes to the larger animals that drift or crawl near the trench floor, depends on a slow, continuous rain of material known as marine snow. It isn't literally snow, and it doesn't fall in flakes. Instead, it forms from the remains of organisms, tiny particles, waste, and organic debris that gradually sink downward. For the life in these depths, this slow descent of nutrients becomes the main source of energy. Near the surface, countless organisms live, die, reproduce, and interact every day. Phytoplankton use sunlight to produce energy. Zooplankton feed on the phytoplankton. Fish, jellyfish, and other animals feed on the zooplankton. Each step in this chain leaves behind particles, pieces of bodies, waste products, and fragments of organic matter. These particles clump together as they sink, forming the marine snow. It begins as small light pieces that drift slowly downward, pushed by currents or consumed by organisms along the way. As the particles fall, they may gather additional material, forming larger aggregates. These can sink faster, but even then the journey takes time. Many are consumed before they reach the deeper layers, making the supply thinner the farther down they travel. By the time marine snow reaches the Midwater Zone, it has already supported countless organisms. Small fish, zooplankton, and filter feeders capture the particles as they drift. Some species migrate upward at night to feed more actively in the upper layers before returning to the darkness during the day. But deeper still, the snow continues falling through water that becomes colder, denser, and darker. At some point, the amount of material decreases significantly, because so many organisms above have already consumed much of it. What reaches the deepest regions is only a fraction of what started at the surface. Even so, this fraction matters. In the trench, every bit of organic material becomes important. The animals that live here are adapted to take advantage of whatever arrives. They do not rely on a constant supply of food, because the supply is never constant. Instead, they rely on slow metabolisms, efficient feeding strategies, and the ability to use small amounts of nutrients effectively. The seafloor at the bottom of the Philippine Trench is covered with fine sediment. This sediment forms from small particles, including marine snow, that collect over long periods. It provides habitat for microorganisms and becomes a surface where organic material can settle. The microbes living in the sediment are essential to the ecosystem. They break down organic matter, releasing nutrients that can be used by other organisms. This process supports a chain of interactions that persists, even though new food arrives in small quantities. Some animals in the trench feed directly on the sediment. Sea cucumbers, for example, move slowly across the seafloor, ingesting sediment and extracting nutrients from the organic particles within it. Their digestive systems are designed to process large amounts of sediment, filtering out the fine organic matter while passing the rest through their bodies. This process helps recycle nutrients and redistribute material across the sea floor. Even though sea cucumbers may seem simple, their role in this environment is important. Amphipods are another group of animals that play a key role in consuming marine snow. These small crustaceans are often some of the most active animals on the trench floor. They scavenge for any organic particles they can find, whether it's marine snow, fragments of dead animals, or larger carcasses that occasionally fall into the trench. Amphipods are well adapted to deep-sea life. Their bodies are flexible, and their digestive systems can handle a wide range of organic material. They're opportunistic feeders, capable of surviving for long periods with minimal food and taking full advantage of any nutrient-rich material that arrives. At times, the deep-sea environment receives a sudden influx of food when a large organism from the upper layers dies and sinks to the bottom. These events, often called whale falls, if the carcass belongs to a whale, create temporary hotspots of activity. For animals in the trench, a large carcass represents a significant resource. Amphipods gather quickly, using chemical cues to detect the presence of the carcass. Their numbers can increase rapidly in the immediate area. Fish, worms, and microbial communities also gather, each taking advantage of different parts of the carcass. The breakdown of such a large food source can support an entire local community for months or even years, depending on its size and the types of organisms involved. Even small carcasses can have a similar effect, though on a smaller scale. Fish, squid, or jellyfish that drift down provide short-term bursts of energy. These events may be infrequent, but when they happen, they shape the feeding patterns of the community. Animals in the trench are adapted to respond quickly when food arrives, using rapid bursts of activity followed by long periods of rest. This approach conserves energy, while still allowing them to benefit from sudden opportunities. Microbial life also takes advantage of these resources. Bacteria colonize carcasses, breaking down tissues and releasing nutrients. Some microbes specialize in consuming fats, while others focus on proteins or other organic materials. The decomposition process can create chemical gradients in the surrounding water, which attract additional organisms. In this way, a single carcass supports a cascade of interactions that extend beyond the immediate area. Certain worms in the deep sea feed on organic material within the sediment or on the surface of the seafloor. These worms may burrow into the sediment, disturbing the layers as they move. Their burrowing activities help mix the sediment, redistributing nutrients and making them more accessible to other organisms. Even though these worms might not be visible in footage captured by submersibles, they contribute significantly to the overall ecosystem. Another important group of organisms in the deep sea are the foraminifera. These single-celled organisms build small shells and live within the sediment. They feed on tiny particles of organic material, helping to break down marine snow further. Their shells accumulate over long periods, becoming part of the sedimentary record. Foraminifera are often used by scientists to study past environmental conditions because their shells preserve chemical signatures that reflect the composition of the surrounding water. The slow pace of life in the trench means that feeding strategies must be efficient. Most organisms here are not built for fast movement. They cannot afford to chase prey across long distances because the energy cost would be too high. Instead, they rely on strategies that allow them to maximize the value of whatever food becomes available. Some species use long sensory appendages to detect organic particles in the water. Others wait passively for food to drift by. Predators may ambush prey rather than pursue it. The scarcity of food also influences the size of animals in the trench. Many species are small because small bodies require less energy. However, size varies widely depending on the species and its ecological role. Amphipods, for example, can grow surprisingly large in deep trenches, sometimes reaching sizes much larger than their shallow water relatives. This phenomenon, known as deep-sea gigantism, may result from factors such as slower metabolism, longer lifespans, and the ability to consume a wider range of food sources. Fish in the trench, such as the snailfish, remain relatively small. Their soft bodies and slow metabolism allow them to survive with limited food. They feed on small crustaceans, worms, and other animals that live on or near the seafloor. Their mouths are often wide relative to their head size, enabling them to capture prey efficiently. They do not rely on speed, but instead use slow, controlled movements to locate and consume food. Feeding in the deep sea also involves cooperation between different levels of the ecosystem. Microbes break down organic material. Small invertebrates feed on the microbes or the partially decomposed material. Larger animals feed on the invertebrates. Each part of this chain depends on the others. Without microbes, nutrients would remain locked in organic particles that larger animals couldn't access. Without small invertebrates, larger animals would lack sufficient prey. The entire system functions because of the interactions between these groups, even though each group operates independently and at its own pace. The rate at which marine snow falls varies depending on surface conditions. During periods of high productivity near the surface, such as during phytoplankton blooms, more organic material forms and sinks. This increased production can lead to temporary increases in food availability in the deeper layers. However, because the journey downward takes time, the effects of these surface events reach the deep sea with a delay. This means the deep sea experiences a lagged response to surface conditions. The organisms here have adapted to this unpredictability by maintaining flexible feeding strategies and slow metabolisms. In addition to marine snow from biological sources, there are inorganic particles that contribute to the deep sea sediment. Dust from land, volcanic ash, and mineral fragments all sink to the bottom. These particles do not provide nutrients, but they become part of the sedimentary environment. Organisms living in the sediment must navigate this mixture of organic and inorganic material to find the nutrients they need. Some species use specialized feeding mechanisms to capture specific types of particles. For example, certain deep-sea sponges filter water through their porous bodies, trapping bacteria and organic particles. The filtering process is highly efficient, allowing the sponges to survive in nutrient-poor environments. Their slow metabolism complements their feeding strategy, enabling them to survive with minimal input. Other organisms use tentacles or appendages designed to capture drifting particles. These appendages may be covered in sticky cells or fine hairs that trap marine snow. The captured particles are then moved toward the mouth for consumption. This method is passive but effective in an environment where particles drift slowly and predictably. The deep-sea ecosystem also benefits from the occasional disturbance of sediment. Subtle shifts caused by earthquakes, landslides, or the movement of water along the trench walls can release pockets of organic material buried in the sediment. These releases provide temporary food sources for animals living nearby. The organisms that can respond quickly to these disturbances often gain an advantage, but even those that move slowly benefit indirectly as the material becomes more accessible to microbes and other small organisms. In this environment, the concept of feeding is not limited to active pursuit of prey. It includes the steady, long-term use of whatever material arrives. Life here must adapt to the idea that food may come in small, irregular amounts. The animals that thrive are those that conserve energy, maximize the value of each meal, and maintain flexible feeding strategies. As we consider the organisms of the Philippine Trench and their relationship to marine snow, it becomes clear that the deep sea is connected to the surface in ways that are subtle but essential. The particles that drift downward carry the energy of sunlight, transformed through countless interactions into the material that sustains life in the depths. Without this connection, the deep sea would be far less hospitable. The slow fall of marine snow becomes the foundation of an entire ecosystem. It supports the smallest microbes and the larger scavengers. It shapes the feeding strategies, metabolic rates, and population structures of the animals that live here. Even though the environment seems isolated, it relies on a chain of processes that begins thousands of meters above. As we continue learning about this environment, it becomes clear that the deep sea survival depends on patterns that span the entire ocean. And as we move forward, the next parts of our journey will continue to show how life adapts to each new challenge presented by these depths. Moving deeper into the Philippine Trench, Another question begins to surface, one that feels almost inevitable when thinking about extreme environments. If food is scarce, if most creatures drift slowly, and if every calorie must be used carefully, how do predators survive here at all? The idea of predation seems almost contradictory in a place where energy conservation defines life. Yet predators do exist, and not just in small numbers. They form an essential part of the ecosystem, fulfilling roles that shape the behaviour and evolution of species around them. They are not predators in the same sense we imagine on the surface. They do not chase their prey through open waters at high speed. They do not rely on sharp eyesight or strong jaws built for immediate impact. Instead, they demonstrate forms of hunting that are efficient, patient, and shaped precisely for the quiet world around them. The absence of sunlight creates an environment where speed and vision lose their usual advantages. Predators cannot rely on visual cues to spot prey from a distance. They cannot use sudden bursts of movement to chase down fast-moving targets because rapid movement consumes too much energy. Instead, their strategies focus on minimizing effort while maximizing opportunity. They wait for the right moment, detect faint disturbances, and use the abilities available to them to capture prey with a kind of precision that looks different from predation at the surface, but is no less effective. One of the most notable deep-sea predators in trench environments is the Hadal snailfish. Although often described as delicate, this fish is an efficient predator adapted perfectly to its environment. Its body may appear soft, but that softness is an asset. It conserves energy simply by existing within a structure that suits the pressure. Its feeding strategy relies on detecting small movements from amphipods and other invertebrates living along the sediment. Instead of pursuing them directly, it positions itself where prey is likely to pass, using its sensitivity to the flow of water to detect movement. Once it identifies a target, it uses a quick suction motion to pull the prey into its mouth. This method minimizes the energy cost and avoids the risks of active pursuit. Many predators in trench environments follow similar patterns. Ambush predation becomes more common than active hunting. Animals wait for prey to approach, using patience as a primary hunting tool. In the deep sea, patience is not merely a behaviour, it is an adaptation. It allows predators to survive long periods without expending energy needlessly. They time their movements carefully, often relying on faint sensory cues to determine when prey is close enough to capture. Chemical sensing is one of the most important tools for deep-sea predators. Because light is absent and vision is limited, chemical signals become a reliable means of locating prey. Prey animals release trace chemicals into the water through waste, decaying tissue, or natural metabolic processes. These chemicals drift with the currents, creating trails that predators can detect. Predators such as amphipods use their antennae to sense chemical gradients. Although amphipods are more commonly recognized as scavengers, they can also act as predators, especially when smaller organisms drift nearby. Some fish species in the deep rely heavily on their lateral line system, a sensory structure that detects changes in water movement. This system allows them to recognize the vibrations caused by swimming prey, or the slight shifts created by animals crawling along the seafloor. The lateral line is so sensitive that it can pick up signals too faint for human technology to detect easily. This gives predators an advantage in an environment where sound and vibration travel farther than visual cues. In some regions of the trench, predators include deep-sea eelpouts, grenadiers, and cusk eels. These fish often have elongated bodies and slow movement patterns. Their mouths can open wide relative to their body size, allowing them to capture prey quickly without needing a strong jaw. Their teeth are often small but sharp enough to hold onto prey long enough to swallow it whole. Many species rely on suction feeding, similar to the snailfish. Suction feeding reduces the energy needed for hunting because the predator draws water and prey into the mouth rather than lunging forward. Some larger predators in the deep sea, such as certain species of grenadiers, feed on a combination of benthic organisms and small fish. They use slow, deliberate movements to explore the sea floor. Their sensory systems help them identify the presence of prey under the sediment or within small crevices. This method of feeding is a compromise between active hunting and scavenging. It allows them to obtain energy without relying solely on chance encounters. Scavenging itself is an important part of predatory behaviour in the trench. In an environment where food is limited, predators rarely specialise exclusively in hunting. Instead, they take advantage of whatever food sources become available. If a carcass falls, predators arrive after the scavengers begin breaking it down, feeding on smaller animals or fragments of tissue. Scavenging reduces the need for prolonged hunting and provides an efficient way to access nutrients. This strategy also fits the overall pattern of energy conservation that defines the deep-sea ecosystem. Even animals with soft bodies can become predators in these depths. Certain deep-sea worms feed on small invertebrates by extending specialized structures that grasp or trap prey. These structures function effectively under high pressure and require minimal energy to operate. The worms often bury themselves in the sediment, waiting for unsuspecting organisms to come within reach. Their bodies remain flexible, allowing them to strike without resisting the surrounding pressure. Another group of predators includes deep-sea crustaceans. Although many crustaceans are scavengers, some species actively prey on smaller organisms. They use their claws or specialized mouth parts to grasp prey. Their exoskeletons are adapted to the deep sea, with reduced mineral content to allow flexibility. Their claws may not be as strong as those of shallow water species, but they are effective within this environment. These predators often move slowly along the seafloor, using their sensory antennas to detect prey. Their movements are efficient, with each step calculated to conserve energy. Some predators rely on bioluminescence. While bioluminescence becomes less common near the trench floor, a few species use small glows to lure prey. The anglerfish is one of the rare examples of a predator that uses a glowing lure in the deep ocean. Even though anglerfish are more common in slightly shallower zones, the principles of their hunting strategy help illustrate how predators can take advantage of light. The lure, positioned near the mouth, attracts curious organisms. When prey approaches, the anglerfish opens its mouth suddenly, capturing the prey using suction. This strategy is efficient and requires minimal movement. Predators in the trench also include species with highly specialized jaws. Some fish have hinged jaws that extend outward to capture prey at surprising distances relative to their mouth size. This adaptation allows them to grab prey that drifts slightly out of reach without moving their entire bodies. The reduced movement saves energy and reduces the likelihood of attracting unwanted attention from other predators. In many cases, predators in the deep sea have large stomachs relative to their body size. This adaptation allows them to store food for longer periods, reducing the frequency with which they need to feed. In an environment where prey encounters may be unpredictable, the ability to consume large meals becomes advantageous. Large stomachs also help predators digest a variety of prey types, from soft-bodied organisms to small crustaceans. Some predators exhibit deep-sea gigantism, growing larger than their shallow-water relatives. Amphipods are a prime example. These crustaceans can reach sizes in the trench that are several times larger than typical coastal species. Their large size allows them to travel longer distances in search of food and to outcompete smaller organisms when carcasses arrive. Their sensory systems are well developed, allowing them to detect chemical cues effectively. This combination of size, flexibility, and sensory ability makes them highly successful predators and scavengers. The behavior of predators in trench environments often reflects patterns shaped by the scarcity of food. They do not waste energy on unnecessary movement. They conserve energy between feeding opportunities. They rely on slow, controlled motions. Their jaws, claws, or appendages operate under low force but high efficiency. Their bodies remain flexible, adapting to the pressure rather than resisting it. One of the most fascinating aspects of deep-sea predators is how they handle competition. Competition is intense because food is scarce, and predators must seize opportunities quickly. When a new food source arrives, predators from different species may converge. Each species adopts a strategy that allows it to feed without losing too much energy. Some approach cautiously, taking only small bites. Others arrive in large numbers, using group behavior to increase feeding efficiency. In some cases, larger predators displace smaller ones temporarily, but this displacement rarely involves direct conflict. Instead, it reflects patterns of resource allocation that have developed over long periods. Predation in the deep sea also shapes the evolution of prey species. Prey animals adapt by developing strategies to avoid detection. Many remain motionless for long periods to avoid creating vibrations. Others bury themselves in sediment or hide within crevices. Some rely on chemical camouflage, releasing substances that mask their presence. Even small changes in behavior can help prey avoid becoming targets. The relationship between predators and prey remains balanced despite the challenges of the deep environment. Predators do not eliminate prey populations because prey species reproduce slowly and in small numbers. The ecosystem maintains stability because predators adapt their feeding strategies to the limited resources. They do not rely on constant feeding. They survive through periods of scarcity, allowing prey populations to recover. In this way, predation becomes another part of the deep-sea cycle. It shapes the behavior, anatomy, and life cycles of species throughout the trench. The behaviors that might seem unusual on the surface, slow movement, long periods of inactivity, soft bodies, and broad diets, become effective strategies for survival. The presence of predators in the trench also highlights the importance of sensory adaptations. Without vision, predators must detect prey using vibration, chemical cues, or subtle movements. These senses operate effectively under pressure, even when other senses become less useful. Predators rely on these systems to maintain accuracy in their feeding strategies. The deep sea's predators demonstrate that life can adapt to extreme environments in ways that may seem counterintuitive from a surface perspective. Hunting does not require speed or strength. It requires patience, sensitivity, and the ability to use minimal energy. The success of predators in the trench comes from their precise adaptations to the conditions around them. As we continue exploring this environment, the interactions between predators and prey help reveal a more complex picture of life in the deepest parts of the ocean. These interactions demonstrate how ecosystems can function under extreme pressure, low food availability, and complete darkness. They show how each species, through its adaptations, contributes to the balance of the environment. As we move toward the deeper walls of the Philippine Trench, the biology of the place slowly blends with something even larger. Down here, life exists alongside forces that operate across vast scales of time and space. These forces are slow, immense, and constant, and they shape the environment just as profoundly as pressure, cold, and darkness do. While the animals survive through careful adaptation, the seabed beneath them shifts, grinds, and rebuilds itself in processes that never stop. These geological movements control the shape of the trench, the flow of water along its walls, and the conditions under which life survives. Understanding this environment fully means looking not just at the organisms living here, but at the tectonic forces that create the trench in the first place. The Philippine Trench exists because of plate tectonics, the movement of the rigid plates that make up the Earth's surface. These plates drift slowly over the asthenosphere, the layer of hot, deformable rock beneath the crust. Their movement is driven by convection currents deep within the Earth. Over millions of years, plates collide, separate, and slide past each other. In the region of the Philippine Trench, one plate is being forced beneath another in a process called subduction. This process is responsible for some of the deepest ocean trenches in the world, including this one. The Philippine Sea Plate and the Sunda Plate meet in this region, and the collision between them forces the denser plate downward into the mantle. As the plate descends, it drags material with it, creating a steep depression in the seafloor. This depression becomes the trench. The depth of the Philippine Trench, reaching more than 10,000 meters in some places, results from the continuous downward movement of the subducting plate. The process is gradual, occurring over millions of years, but the outcome is dramatic. The trench forms a boundary between the plates, marking a zone where the Earth's crust is pulled downward and consumed into the deeper layers of the planet. This subduction process does not proceed smoothly. The plates do not glide past each other without resistance. Instead, they experience friction, build-up of stress, and occasional release of that stress in sudden shifts. These shifts create earthquakes. In the deep ocean, these earthquakes are sometimes referred to as megathrust earthquakes, because they occur where one plate is thrust beneath another. These events are among the most powerful earthquakes on the planet. They release enormous amounts of energy, reshaping the surrounding geology and influencing the conditions in the deep sea. The Philippine Trench region is known for frequent seismic activity. This activity does not always produce large earthquakes. Many are small and unnoticed by people on land, but they still matter in the deep sea. Even small movements of the plates can shift sediment, change local currents, or disturb the sea floor. These disturbances affect the organisms that live here, altering their habitats and sometimes prompting temporary changes in behaviour. Larger earthquakes can have more significant effects. They may cause underwater landslides, create new cracks in the seafloor, or disrupt the flow of water through the trench. Undersea earthquakes also influence the chemistry of the environment. When the seafloor shifts, it can release trapped gases or minerals from the sediment. These materials diffuse into the water, creating temporary changes in chemical composition. Microbial communities respond quickly to these changes because they rely on chemical gradients for energy. In some cases, shifts in the seafloor expose new surfaces where minerals interact with seawater, creating chemical reactions that support entire microbial ecosystems. These interactions form part of the deep sea landscape, providing resources that larger animals may eventually benefit from. The idea of architecture in this context refers to the long-term shaping of the ocean floor. Over millions of years, subduction zones carve deep trenches, build mountain ranges and form volcanic arcs. These features influence currents, habitats, and the distribution of life. The Philippine Trench is one of the features created by these tectonic forces. Its depth, shape, and internal structure all reflect the history of plate movement. The trench is not a fixed structure. It changes slowly over time. The walls can steepen or collapse. The floor can accumulate sediment or be cleared by landslides. These changes alter the environment for the organisms living here. Some of the most interesting geological features in the trench are the faults that run along the plate boundary. These faults mark zones where the crust fractures and shifts under pressure. They may be small, extending only a short distance, or they may run for hundreds of kilometers. The faults allow the plates to move relative to each other. When stress builds up along a fault, it can be released suddenly in an earthquake. The pattern of faulting in the trench reflects the complex interactions between the plates. Mapping these faults helps scientists understand how the trench formed and how it continues to evolve. Undersea earthquakes also generate seismic waves that travel through the water and the Earth's crust. These waves can disturb the sediment layers on the trench floor. Sediment that has accumulated over long periods may be reshuffled, creating new layers or exposing older ones. This reshuffling can influence the availability of nutrients for benthic organisms. When sediment shifts, buried organic material may become accessible again, providing a temporary increase in food for microbes, worms, and other small organisms. The trench walls themselves are shaped by a combination of tectonic forces and sedimentation. As the plate descends, it pulls sediment downward along the trench walls. Some of this sediment accumulates at the bottom, forming a thick layer of fine material. Other portions slide or slump, creating unstable slopes. These slopes may collapse during earthquakes, sending cascades of sediment downward. Such events can bury organisms living on the trench floor or create new areas where fresh, nutrient-rich sediment becomes available. The seafloor remains dynamic, even though it may appear still in submersible footage. Volcanic activity also plays a role in the region. Although the Philippine Trench itself is not volcanic, the subduction process contributes to the formation of volcanic arcs nearby. The descending plate heats as it moves deeper into the mantle. This heat causes water and other materials to be released from the plate. These materials lower the melting point of the overlying mantle, leading to the formation of magma. The magma rises, forming volcanic arcs at the surface. While these volcanoes are not located within the trench, their activity influences the chemistry of the surrounding ocean and the distribution of nutrients. Hydrothermal fluids may also reach the deep sea in certain locations. These fluids carry minerals that can support unique microbial communities. While hydrothermal vents are more common along mid-ocean ridges, subduction zones can also create conditions for venting. If such vents occur near the trench floor, they provide additional sources of chemical energy for organisms. These environments host specialized microbes that thrive on the minerals released from the Earth's crust. Although vents in the Philippine Trench region are not as well documented as those in other parts of the Pacific, geological processes suggest their presence is possible. The geology of the trench does more than shape the physical environment. It also influences the behavior of deep-sea currents. As water moves along the trench walls, it interacts with the steep topography. These interactions create areas of slow movement and areas where water flows more rapidly. The movement of water helps distribute nutrients, oxygen, and heat. In the deep ocean, even small changes in current patterns can influence the distribution of organisms. Certain species may prefer areas where water movement is minimal, allowing fine particles to settle. Others may inhabit areas where currents deliver fresh material from above. Even though the deep sea lacks the turbulence of surface waters, the currents here remain essential. They transport marine snow, redistribute sediment, and allow chemical gradients to form. The trench acts as a channel that directs water movement along its length. Earthquakes can alter these currents temporarily by shifting the seafloor or creating new pathways. Over time, these changes shape the habitats available to deep-sea organisms. The architecture of the trench also influences temperature distribution. The deep ocean remains cold, generally just above freezing, but small variations in temperature occur depending on water movement and geological activity. These variations may affect metabolic processes in deep-sea organisms. Temperature changes slowly, but even slight shifts can influence how microbial communities function or how oxygen is distributed. Geological activity also affects how gas hydrates form in the sediment. Gas hydrates are crystalline structures where gas molecules, such as methane, become trapped within a lattice of water molecules. These structures form under high pressure and low temperature, conditions common in deep-sea trenches. When earthquakes disturb the sediment, gas hydrates can break apart, releasing methane into the water. Microbes consume the methane, forming part of the deep-sea food web. This process links geological activity with biological energy cycles. The trench acts as a natural recorder of geological history. The layers of sediment that accumulate on its floor contain information about past earthquakes, volcanic eruptions, and changes in ocean circulation. Scientists study these layers to reconstruct the geological timeline of the region. Each layer represents a period of deposition, marked by variations in particle size, composition, and chemical signatures. Disturbances caused by earthquakes appear as mixed or displaced layers. These signs help identify the magnitude and frequency of past seismic events. As we continue observing this environment, it becomes clear that life here is shaped not only by the constant physical conditions, but also by the occasional disturbances. Earthquakes may be infrequent, but their impact lasts. They redistribute material, create new habitats, and expose layers of sediment that were previously buried. These events influence the long-term evolution of the ecosystem. Species that can adapt to sudden changes gain an advantage. Those that rely on stable conditions may struggle. Some organisms become indicators of geological activity. Their behaviour or distribution may change following an earthquake. Amphipods may gather in areas where fresh organic material becomes available. Worms may take advantage of newly exposed sediment. Even microbes respond quickly because they rely on chemical gradients that shift after seismic events. By studying these changes, researchers gain insight into how the trench environment responds to natural disturbances. The trench's shape, depth, and steep walls reflect millions of years of tectonic activity. These geological features influence every aspect of life here. They determine the pressure conditions, the movement of water, the distribution of nutrients, and the types of habitats available. Without the subduction process, the trench would not exist, and the organisms adapted to extreme depths would not have their unique environment. Understanding these forces adds depth to our view of the ecosystem. The animals living here are not merely surviving in isolation, they are part of a landscape shaped by immense forces. The quietness of the deep sea hides the slow, powerful movements that continuously alter its structure. These movements, though gradual on human timescales, have created one of the most extreme environments on Earth. As we continue into the next part, the relationship between life and these geological forces becomes even clearer, showing how survival here depends not only on biological adaptation, but also on the shifting foundation beneath it. As we continue deeper into the Philippine Trench, the sense of how improbable life here seems only grows stronger. Every part of this environment pushes organisms toward limits that are hard to imagine from the surface. Pressure reaches levels that would destroy most biological structures. Temperatures hover just above freezing. Food is scarce, drifting down in small, unpredictable amounts. Light never reaches this far, and the geological forces beneath the seafloor shift at a pace that can reshape habitats without warning. All of these factors combine to create a world that appears too hostile for life. Yet the trench is filled with organisms that not only survive but have adapted so thoroughly that these conditions form the basis of their existence. The key to this survival lies in slow, precise adjustments that occur over long stretches of evolutionary time. Organisms that reach the trench do so through generations of incremental adaptation. Every trait that persists is one that enhances stability in an environment where stability is difficult to achieve. Even small changes in body structure, chemistry, or behaviour can influence whether a species can withstand the pressure, find food, and reproduce. Most of the organisms living in the trench experience life at a pace far slower than animals in shallow water. Metabolic processes proceed gradually because energy must be conserved. Slow metabolism is not a disadvantage here. It becomes an advantage because it reduces the need for frequent feeding. The scarcity of food makes this slow pace essential. Organisms that expend energy rapidly would struggle to survive during long periods without nourishment. In contrast, those with reduced metabolic rates can endure extended intervals of scarcity. This slow pace affects growth as well. Many deep-sea animals grow slowly and reach maturity later than their shallow water relatives. Their growth is steady and controlled, matching the availability of resources. Slow growth also minimizes the risk of disruptions caused by sudden changes in the environment. When an earthquake shifts sediment or alters chemical gradients, organisms with slow growth and stable physiology can adjust more easily. Reproductive strategies in the trench reflect these demands. Some species produce fewer offspring but invest more energy in each one. A single egg or larva receives resources that allow it to survive under harsh conditions. This investment increases the chances that at least some offspring reach maturity. Other species produce many small eggs or larvae, allowing a wide distribution across the deep-sea environment. In both cases, the strategy reflects the unpredictable nature of the deep ocean. Success comes not from rapid reproduction, but from steady persistence. Even the basic structure of deep-sea organisms reveals their adaptability. Soft bodies, flexible skeletons, and reduced airspaces allow animals to withstand pressure that would be unimaginable elsewhere. As noted earlier, air pockets pose a major risk under pressure. By eliminating these pockets and relying on tissues that compress evenly, organisms avoid the risk of collapse. Pressure becomes something their bodies accommodate, not something they resist. The stability of this strategy allows species to thrive where rigid structures would fail. Chemical adaptations are just as important. The molecules that make up deep-sea organisms must remain functional under high pressure and low temperature. Proteins must maintain their shape to continue working. Enzymes must remain active. Cell membranes must remain fluid. To solve these challenges, deep-sea species produce molecules that stabilize proteins or prevent membranes from becoming too rigid. These biochemical tools allow cells to function despite the extreme environment. Without these adaptations, fundamental biological processes would stop. Microbial life demonstrates some of the most impressive adaptations. Microbes living in the trench possess enzymes that functioned under conditions that would inhibit most other organisms. Some microbes use chemical energy derived from interactions between minerals and seawater, providing a source of energy independent of sunlight. These processes support entire communities. Larger animals feed on these microbes directly or indirectly. Because microbial populations can respond quickly to changes in chemical conditions, they form the foundation of resilience within the trench ecosystem. One of the most significant challenges in the deep sea is the scarcity of food. Marine snow provides a slow, steady trickle of nutrients, but the amount decreases dramatically with depth. Organisms that survive in the trench must make use of every opportunity. Many species have evolved feeding strategies that allow them to consume a wide range of material. Amphipods, for example, can feed on organic particles, decaying tissue, or even the remains of other amphipods. This versatility increases their chances of survival in an environment where specialized diets would be risky. Other species rely on highly efficient digestive systems. Sea cucumbers process sediment to extract nutrients from even the smallest organic particles. Their digestive tracts operate continuously, taking advantage of whatever material settles on the seafloor. This strategy ensures a steady intake of nutrients, even when the supply is limited. Their feeding behavior also helps recycle nutrients, supporting the broader ecosystem. Predator-prey interactions add another layer to survival. Predators must conserve energy while still finding food. They rely on strategies such as ambush hunting, slow stalking, or suction feeding to capture prey efficiently. These methods reduce the energy cost of feeding. Prey species, in turn, adopt behaviors that help them avoid detection, such as remaining motionless or burying themselves in sediment. These interactions form part of a stable cycle that persists even with limited resources. The ability to endure long periods without food is a defining characteristic of many trench animals. Some species can go weeks or months between meals. They rely on energy stores in their tissues or reduce their activity levels to conserve energy. This ability becomes especially important when sudden disturbances reshape the environment. After an earthquake, for example, sediment may shift, burying food sources. Animals that can endure these temporary shortages gain a long-term advantage. The trench environment also demands resilience in the face of sudden changes. Geological activity, though infrequent on human timescales, has immediate effects when it occurs. Landslides can expose new layers of sediment, changing the availability of nutrients. Gas hydrates can release methane, altering chemical gradients. These changes create temporary opportunities or challenges for organisms living nearby. The species that persist are those that can adjust quickly, either by taking advantage of new resources or by reducing activity until conditions stabilize. Some species show remarkable flexibility in their behavior. Amphipods, for example, move across the trench floor in search of food, exploring areas where fresh sediment or decaying material has become available. Their ability to respond quickly to chemical cues allows them to locate resources efficiently. They can shift their behavior depending on the environment, feeding aggressively when food is abundant and conserving energy when it is scarce. Other species remain more stationary but still exhibit adaptability. Sea cucumbers move slowly, but can shift their position when sediment conditions change. Snailfish adjust their hunting strategies based on the availability of prey. Worms alter their burrowing patterns to reach newly exposed material. These behaviours reflect a broader theme of flexibility and restraint. The stability of the deep-sea environment also contributes to survival. While food is limited and disturbances occur, the basic conditions remain constant. Temperature stays near freezing, pressure stays high, light remains absent. These stable conditions allow species to evolve traits that match the environment precisely. Deep-sea organisms do not need to adapt to seasonal changes or rapid temperature swings. Their energy can be directed toward survival strategies rather than constant adjustment to shifting conditions. Reproduction in the trench follows similar patterns of stability. Some species mate once and produce eggs that take years to develop. Others reproduce more frequently but produce fewer offspring. The timing of reproduction may depend on environmental cues such as chemical changes or the availability of nutrients. These strategies ensure that offspring have a chance to survive even in a demanding environment. The slow pace of life means that reproductive success depends on long-term stability rather than short bursts of production. Many deep-sea species also exhibit longer lifespans compared to animals living in shallower waters. A slow metabolism reduces wear and tear on tissues. Lower activity levels reduce stress. These factors contribute to extended lifespans that allow organisms to reproduce multiple times over long periods. Longer lifespans also reduce the need for rapid population turnover. This stability supports the balance of the ecosystem. Another important factor in survival is the ability to navigate the darkness. Without light, organisms rely on other senses to find food, avoid predators, and locate mates. Sensory systems such as the lateral line in fish detect changes in water movement. Chemical receptors identify the presence of organic material or other animals. These senses operate efficiently under high pressure and allow organisms to interpret their surroundings accurately. The absence of light becomes less of an obstacle when sensory systems are refined for this environment. Some species use minimal bioluminescence to provide simple signals. These signals may help individuals identify members of their own species or warn predators. The use of bioluminescence is controlled and sparse because too much light risks attracting unwanted attention. Even small flashes can influence behavior in the deep sea, demonstrating how organisms use energy carefully and strategically. Survival also depends on cooperation between different components of the ecosystem. Microbes break down organic material. Small invertebrates feed on microbes or organic particles. Larger animals feed on the invertebrates. Each group contributes to the stability of the food web. If any component were removed, the balance would shift. Yet the ecosystem remains resilient because each group performs its role consistently and efficiently. The trench environment reveals how life can persist in places that appear inhospitable. The organisms here are not living on the edge of survival. They are well adapted to their conditions. Their survival does not represent a struggle against the environment. Instead, it reflects a long process of adaptation that aligns their traits with the demands of the deep sea. Life in the trench continues because it has become part of the structure of this environment, matching its stability, its slow pace, and its challenges. As we continue moving through this region, the picture becomes even clearer. The relationship between biological adaptation and environmental forces forms a system that, while extreme, supports its own kind of stability. The next steps of the journey will explore the remaining mysteries of this quiet, demanding world. As the journey through the Philippine Trench continues, the sense that there is still far more unknown than known becomes difficult to ignore. The deeper we go, the clearer it becomes that even the most advanced instruments, the longest expeditions, and the most detailed surveys have only scratched the surface of this place. The Hadal Zone remains one of the least explored environments on Earth. The reasons for this are simple. The conditions make access difficult. The pressure complicates equipment design. The darkness limits visibility. The remoteness of the region creates logistical challenges. All of these factors combine to ensure that large portions of the trench remain unobserved, waiting for future exploration. The unknown elements of this environment fall into several categories. Some are biological, involving species that have yet to be discovered or understood. Others are geological, linked to the structure of the Earth and the processes that shape the trench. Still others are chemical, involving reactions and interactions that occur under conditions far beyond what humans typically encounter. Each of these areas contributes to the broader sense of mystery. The biological unknowns are among the most intriguing. Deep-sea expeditions using remotely operated vehicles or autonomous submersibles occasionally capture footage of organisms that have not been identified. These glimpses may show unusual shapes or movements. Sometimes they show known species behaving in unexpected ways. Other times they reveal organisms that appear only briefly before disappearing back into the dark. Because expeditions to these depths are rare, scientists often gather only limited data on these sightings. Without continuous observation, determining the species' full range of behaviours, feeding habits, or ecological roles becomes difficult. One reason so many species remain undocumented is the physical structure of the trench. The steep walls, narrow rifts, and isolated pockets create small habitats that may support unique organisms. These isolated habitats can differ in temperature, chemical composition, or sediment structure, allowing distinct species to evolve in each area. Some organisms may live in specific depth ranges and rarely move beyond them. Others may inhabit crevices or depressions that are difficult for submersibles to reach. These limitations mean that even well-planned expeditions can miss species that live only meters away from where the cameras explore. Microbial life in the trench remains another area filled with questions. Microbes dominate many deep-sea ecosystems. They break down organic material, process chemical compounds, and support larger organisms. In the trench, microbes may rely on sources of energy that human researchers still do not fully understand. Some microbes use methane or other gases released from sediment disturbances. Others rely on chemical reactions involving minerals from the Earth's crust. Because laboratory conditions rarely replicate deep-sea pressure and temperature exactly, cultivating these microbes for study can be difficult. As a result, many remain unidentified, and their metabolic processes remain partially unknown. The sediments on the trench floor also hold clues about microbial diversity. Layers of sediment accumulate slowly over long periods. Each layer contains different mixtures of minerals and organic material. Microbial communities respond to these layers, forming distinct groups with different functions. Some break down organic carbon, others consume dissolved gases. Still others produce compounds that support larger organisms. Because sediment layers can shift or become disturbed during earthquakes, the interactions between microbes and minerals can change rapidly. These shifts create new habitats that scientists have only begun to explore. Larger animals also present mysteries. Deep-sea fish such as snailfish, eelpouts, and grenadiers have been observed at various depths. However, their full ranges remain unknown. Some species may travel between depth zones depending on feeding opportunities. Others may remain stationary in specific regions. Without continuous monitoring, understanding their movement patterns remains challenging. Behaviour such as mating, territoriality, or long-range migration is difficult to document because submersibles cannot remain at depth for extended periods without refueling or maintenance. The trench may also host entirely unknown species of invertebrates. Worms, mollusks, crustaceans, and other small organisms may inhabit specific microhabitats. These animals could have adaptations that differ significantly from known species. For example, some worms may use chemosynthesis instead of relying on marine snow. Some crustaceans may incorporate unusual minerals into their exoskeletons. Without collecting samples, these species remain hypothetical. But because deep-sea expeditions often retrieve specimens during sediment sampling, scientists expect that many unknown species remain in the trench. Geological mysteries also play a significant role in shaping the trench. The subduction process that forms the trench continues without a clear endpoint. The plates move slowly, changing the trench's shape over geological time. However, the details of this movement remain uncertain. Mapping the trench floor is difficult because of its depth and steep structure. Many features may be hidden by sediment or located in areas where instruments cannot reach. Faults, cracks, and folds in the rock may shift suddenly, but detecting these shifts requires continuous monitoring equipment. Deploying such equipment at extreme depth presents major engineering challenges. Another geological mystery involves the distribution of deep-sea minerals. In some trenches, mineral deposits form from interactions between seawater and the Earth's crust. These deposits can include rare metals, hydrocarbons, and crystalline structures. The exact distribution and formation processes of these minerals remain partially unknown in the Philippine Trench. Because collecting samples from the deepest areas is expensive and time-consuming, detailed surveys occur infrequently. As a result, scientists have only general models for how minerals form here. Undersea earthquakes in the trench also produce mysteries. Although the general process of plate movement is understood, predicting the exact behaviour of faults remains difficult. Small variations in pressure, temperature, or rock composition can influence how the plates interact. These variations may create localized zones where stress builds up or releases unpredictably. Without direct observation, understanding these zones remains theoretical. Deep-sea sensors can detect seismic waves, but cannot always determine their exact origin or effect on the surrounding environment. Chemical mysteries are equally important. At extreme depth, chemical reactions occur differently than at the surface. High pressure influences how molecules interact. Some reactions that would be slow or impossible at normal pressure may occur more readily here. Other reactions may proceed differently because of the low temperature. These chemical differences influence everything from mineral formation to microbial metabolism. They also affect how nutrients move through the ecosystem. One chemical mystery involves the movement of methane through the sediment. Methane hydrates form when methane becomes trapped within ice-like structures under pressure. When earthquakes disturb the sediment, these hydrates can release methane. Microbes consume some of the methane, but the rest may diffuse into the water. The long-term impact of these releases remains unclear. Because methane influences microbial communities, changes in methane availability may reshape parts of the ecosystem. Scientists have measured methane concentrations in some areas, but the full patterns remain unknown. Another chemical mystery involves the interaction between minerals and seawater in areas where the plate is actively subducting. As the descending plate heats up, minerals release fluids that may rise through cracks in the seafloor. These fluids can contain unusual chemical compounds that support microbial life. In some subduction zones, hydrothermal vents form as these fluids reach the surface. The presence and distribution of such vents in the Philippine Trench remain uncertain. If vents exist here, they could support microbial communities unlike those seen in other parts of the ocean. The physical environment also raises questions. For example, the movement of water along the trench walls may influence nutrient distribution, but the details of these currents are not fully mapped. Some currents may be driven by tidal forces, while others depend on global ocean circulation. Because measuring current patterns at extreme depth requires long-term sensors, data remain limited. The structure of the trench, with its steep walls and narrow passageways, makes water movement more complex. Small variations in current patterns can influence where marine snow accumulates, where sediment shifts, or where organisms gather. The darkness of the deep sea also presents mysteries. Although bioluminescence becomes less common near the trench floor, some organisms may still produce faint glows. These glows may be too dim or too brief to capture on video. Some microbes produce chemical light as part of their metabolism. If such microbes exist in large enough numbers, they may create subtle light patterns that have not yet been documented. Detecting such patterns would require highly sensitive equipment that can function under pressure for extended periods. Another source of mystery involves the long-term stability of deep-sea populations. Many species in the trench have slow metabolisms and long lifespans. Their populations adjust gradually to changes in nutrient availability or environmental conditions. Without long-term observation, understanding these adjustments remains difficult. Some populations may fluctuate over decades, influenced by changes in surface productivity or geological activity. Others may remain stable for long periods, reflecting the slow pace of life in the deep. The trench also holds mysteries about the movement of species between depth zones. Some organisms may migrate vertically over long periods, moving up and down the water column depending on temperature, chemical conditions, or life stages. These movements are difficult to track because submersibles rarely follow animals long enough to observe long-term behaviour. Tagging animals in the deep sea is challenging because tags must withstand pressure and remain functional for years. Without this technology, understanding movement patterns remains a future goal. An additional unknown involves how climate change will influence the trench. While the deep sea remains insulated from short-term surface changes, long-term shifts in temperature, ocean circulation, or nutrient patterns may eventually reach these depths. The timing and extent of these influences are uncertain. Changes in surface productivity may affect the amount of marine snow reaching the trench. Alterations in current patterns may redistribute nutrients. Understanding these processes requires long-term monitoring that has only recently begun. The Philippine Trench also presents mysteries related to geological age and sediment history. Sediment cores reveal layers representing thousands or millions of years. Each layer contains clues about past ocean conditions, volcanic events, or changes in marine life. However, sampling these layers remains difficult because retrieving cores from extreme depths requires specialized equipment. Even when samples are obtained, interpreting them can be complex because the sediment may have been disturbed by earthquakes or landslides. Many questions about past climate patterns and geological events remain unanswered. It is also possible that entirely new ecosystems exist within the trench, isolated from the rest of the ocean. Small pockets of water trapped within geological structures may have unique chemical compositions. These microenvironments could support distinct microbial communities. Without direct exploration, their existence remains speculative. But because similar isolated environments have been found in other oceanic regions, the possibility remains open. The deep sea remains one of the last frontiers on Earth. The Philippine Trench embodies this idea more than almost any other location. The combination of extreme depth, pressure, and remoteness ensures that much of it remains hidden. But each expedition, each sample, and each observation adds to our understanding. The mysteries that remain are not obstacles but opportunities. They reflect the limits of current knowledge and the potential for future discovery. As we move forward, the sense of unknown becomes part of the environment itself. It shapes the experience of exploring the trench, reminding us that even in the most extreme environments, life continues to evolve, geological forces continue to operate, and the details remain waiting for future observation. Whenever you're ready, we'll continue into the next stage of this journey and follow the slow ascent back toward the upper layers. As the exploration of the Philippine Trench continues, the path ahead begins shifting upward. It isn't a fast transition, and it doesn't feel like a departure from the environment below. Instead, the movement resembles a gradual easing of conditions that have been constant for so long. The pressure remains immense, the darkness remains complete, and the cold continues without change. But step by step, meter by meter, the shift begins. What seemed distant before begins becoming slightly more familiar, though still far removed from the surface world. Leaving the deepest parts does not mean leaving the trench behind. The ascent reveals additional layers of this vertical environment. Each depth brings small changes that affect the organisms living there, the chemistry of the water, and the movement of marine snow. Even though these changes may appear minor compared to those between the surface and the deep, they still represent significant shifts for species that have adapted to specific ranges. The ascent becomes an opportunity to consider how the environment transitions, how pressure decreases with every step upward, and how each layer supports its own forms of life. At the lowest depths, conditions remain harsh. The pressure stays intense enough that any organism must possess specialized adaptations. Soft-bodied species still dominate, and creatures continue depending on small amounts of nutrients. But as the ascent continues, the pressure begins decreasing gradually. There is no sudden release. Instead, the change is steady and predictable. Organisms living in slightly shallower regions have bodies built to withstand high pressure, but they no longer require the extreme structural flexibility found in the deepest species. Their anatomy reflects this middle ground. Instead of eliminating all rigid structures, some species retain small amounts of mineralization that provide additional support. This gradual transition shows how organisms fill each available niche. One of the first changes that becomes noticeable as the ascent continues is the increased movement of water. Near the trench floor, the water often feels still. Currents exist, but they move slowly, influenced by the shape of the trench and the density of the water. Higher up, currents strengthen slightly. These movements transport marine snow more efficiently, carrying particles into different regions. They also influence how organisms move. Some species rely on these currents to deliver food, drifting within the flow and capturing particles as they pass. Others anchor themselves in place, allowing the movement of water to bring resources to them. These currents also affect the distribution of oxygen. The deep ocean contains oxygen, but the movement of water determines how evenly it spreads. Upward in the trench, slight improvements in water movement help distribute oxygen more consistently. This change supports species that may have higher oxygen requirements than those living at the deepest points. The gradual increase in oxygen availability influences metabolic processes, allowing some organisms to become slightly more active without increasing their energy consumption too much. As the ascent continues, different species begin appearing. Some are familiar from earlier parts of the journey, but others represent new groups adapted to mid-Hadal depths. These organisms experience intense pressure, complete darkness, and low temperatures, but they have access to more consistent nutrient flow than those at the trench floor. Amphipods remain abundant, but their sizes vary more. Some become smaller, reflecting the slight increase in energy available in these layers. Others remain large, especially those that feed on drifting carcasses or larger particles of marine snow. Fish species become more diverse in these regions. Some snailfish still appear, though they may differ slightly from those seen at the very bottom. Their bodies remain soft, but their behaviour may include more movement. They feed on amphipods, small crustaceans, and worms living within the sediment. Their ability to navigate using sensory cues remains essential because light has still not returned. But they may encounter more varied terrain along the trench walls, including ridges, crevices, and slopes. Worms continue playing a major role in the ecosystem. Some species feed directly on the sediment, while others capture particles drifting through the water. Their burrowing and feeding behaviour helps maintain the structure of the seafloor. As sediment shifts, worms redistribute nutrients and create small habitats for microbial communities. Each movement they make influences the landscape subtly but consistently. Microbial life remains abundant throughout these depths. Microbes continue breaking down organic material, producing chemical byproducts that other organisms use. Some take advantage of chemical gradients created by shifting sediments or slow release of minerals from the trench walls. These gradients may vary slightly as the ascent continues, providing additional niches for microbial species. The variety and density of microbes help support the entire food web, even when larger organisms remain sparse. At these depths, the sediment composition begins changing. While the trench floor collects fine particles that accumulate slowly, Higher areas may contain a mixture of fine sediment and larger fragments. These fragments may come from landslides, rockfalls, or shifting material along the trench walls. The variety of sediment supports different forms of life. Some organisms prefer soft sediment where they can burrow easily. Others use small rocks or debris as shelter. Even minor variations in sediment type influence which species appear in each region. As the ascent continues further, the pressure keeps decreasing slowly. Even though the difference may not seem dramatic from a human perspective, organisms at each depth experience the environment precisely. Species adapted to deeper conditions may not tolerate these changes, so they remain below. Species adapted to this middle range begin to dominate, each filling a role in the expanding food web. The availability of food increases slightly in these depths, because more marine snow remains intact as it drifts downward. These particles support larger communities, including filter feeders, scavengers, and predators. Some species specialize in capturing the smallest particles, while others take advantage of larger fragments. The increased availability of food supports a more stable population structure. Organisms do not need to endure as many extended periods of scarcity, though scarcity still defines much of the deep sea. The ascent also reveals how geological features influence the ecosystem. The trench walls contain variations in slope and composition. Steeper sections may be unsuitable for certain animals, while flatter areas support more sediment. Crevices and cracks provide shelter for small organisms. Microbial mats may form in areas where minerals interact with seawater. These mats provide food for some species, adding another layer to the complex structure of the environment. While the geological forces that shape the trench remain active, their influence becomes more apparent at these shallower depths, because sediments shift more visibly. Small landslides move material downward, creating temporary changes in habitat. Animals respond by relocating or adjusting their feeding strategies. The stability of the environment depends not only on long-term processes, but also on these short-term events. Continuing upward, light remains absent, but faint changes in the structure of the water column begin appearing. Temperature still stays low, though slight variations may occur depending on the movement of water and the influence of deeper currents. These changes do not create large differences, but they influence the chemistry of the water. Some species respond to these changes by adjusting their behaviour. For example, certain fish may move vertically within narrow depth ranges, where conditions best match their physiology. The ascent eventually reaches depths where bioluminescence becomes more common. Even though the glow remains faint, it becomes part of the environment once more. Organisms use bioluminescence carefully, producing small signals that serve specific purposes. Some use it for communication, others use it to attract prey, some use it defensively. The presence of bioluminescence introduces a subtle visual element to an environment that has remained dark for so long. These glows do not illuminate the surroundings, but create points of reference for animals sensitive to them. Jellyfish and other gelatinous organisms appear more frequently in these regions. Their bodies drift with the currents, capturing particles or small prey. Their slow movements match the pace of the environment, conserving energy while taking advantage of drifting food. Some species produce bioluminescence, creating short pulses of light. These organisms play an important role in transferring energy through the water column as they consume smaller species and become prey for larger ones. Further upward, the water begins to show small signs of change in the density of organisms. While still sparse compared to shallower regions, the increased presence of midwater species becomes noticeable. The ecosystem grows more diverse in its structure. Different organisms occupy different layers within the water column. Some species stay close to the sediment, others drift in midwater. Some move vertically in search of food. This part of the ascent also provides more opportunities to observe the influence of global ocean circulation. Deep currents driven by temperature and salinity travel through these layers. These currents help distribute nutrients across long distances. They connect the trench environment to broader regional patterns. Although these currents move slowly, they remain an essential part of sustaining deep-sea life. Their movement shapes the distribution of sediment, nutrients, and even microbial communities. Even though the ascent continues slowly, the pressure remains high enough that few human-made devices can withstand it without specialized engineering. The difficulty of exploring these depths contributes to the mysteries that remain. Even in regions where organisms appear more frequently, visibility remains limited. Submersibles capture only narrow slices of the environment. The ascent reminds us that the deep sea remains largely unexplored. As pressure continues decreasing, organisms from the slightly brighter mid-ocean layers eventually become more common. Fish with larger eyes, though still adapted to low light, begin appearing. These species rely on vision more than those in deeper layers. They take advantage of faint light from bioluminescent organisms, or the small amount of light that diffuses from upper layers. Their feeding strategies include capturing small fish, zooplankton, or crustaceans. Zooplankton become more abundant as the ascent brings the environment closer to the mesopelagic zone. These small organisms play a significant role in the global carbon cycle. They consume phytoplankton during their vertical migrations and release waste that becomes part of marine snow. Their presence supports a wide variety of predators. As the ascent approaches higher levels, marine snow becomes denser. The particles are less degraded because they have travelled a shorter distance. These particles support organisms that specialise in capturing small bits of organic material. Filter feeders become more diverse. Their structures allow them to collect particles efficiently. The increased availability of food supports larger populations and greater biodiversity. Throughout this upward movement, the transition remains gradual. No sudden changes mark the shift from one layer to another. The deep sea maintains its slow, steady pace. Organisms move deliberately. Sediment settles in quiet patterns. Currents travel consistently through long distances. Even as more life appears, the environment retains its calmness and stability. The significance of this ascent lies not in leaving the depths behind, but in seeing how the layers connect. Each depth supports different adaptations, feeding strategies and interactions. The trench floor relies on marine snow originating near the surface. The midwater supports the downward flow of nutrients to deeper regions. Microbial communities ensure that no resource remains unused. The entire system operates as a continuum rather than separate zones. As the journey continues upward, the sense of how vast and continuous this world is becomes clearer. The deep sea does not end abruptly. It spreads outward, upward, and across the globe, connecting every ocean. The life found here represents only a small part of the global ecosystem, but remains essential for understanding how the ocean functions as a whole.